So in the last session, we talked about kernels, right? What kernel trick will basically do is instead of transforming the points to higher dimensions, it tries to find out the similarity between the points in the original space as if they were transformed to higher dimensions and then similarity is calculated, right? So that is what the kernel trick is. So we do have different kernels that are available. Such kind of kernel is polynomial kernel. So we do have different types of kernels available. But most frequently used kernels are polynomial kernel and radial basis kernel. So those two are some things which are something that we will see today. But the main intention of the kernel is that to reduce that complexity of or computational complexity of transforming the points to higher dimensions and calculating the similarity is is minimized, and the similarity is calculated in the original space itself, right? That's what kernels will basically do. How does this polynomial kernel actually will do that is, so the base formula of a polynomial kernel is given as this. It's like a cross b plus r whole to the power of t. So A and B refers to two different observations in the data set. So A and B in this particular kernel formulation is given as the two observations in your data set. Okay. So if these are like in higher dimensions, that become a dot product. A will be in vector, B will be vector, and the A cross B will become the dot product between the two observations. As this is one dimensional space, so this would be just an integer value, right? So on x-axis we are representing 2 points, and those two will have some integer values. So we will just multiply them. Plus r determines the coefficient of the polynomial. So it can be any coefficient. So we again r and d will be determined using the cross validation again. So again, you cannot actually determine, you cannot actually put some constant to it. R and d will be determined by cross validation. As I told you, most of the tuning in machine learning will happen only through cross validation. So we have to train the model, see how the model is behaving, or find out the accuracy of the model and change the values of R to other value. So it can be some constant. R is determines the coefficient of the polynomial. D sets the degree of the polynomial. So when D is equal to 2, it is said as second degree polynomial kernel. If it is the third degree polynomial kernel. So that is what basically the formulation says. A and B are two observations on the original dimensional space, and R is the coefficient of the polynomial, and D is the degree of the polynomial. So if you take an example now, as I told you, kernels will try to find out the the similarity in the original dimension space. But in general, that similarity is just equal to the similarity of transforming the point to higher dimensions and then finding out the similarity in the higher dimensions. I already showed you, right? So we have 2 points in the 2D space. We transformed them to three-dimensional space, and then we calculated the similarity. Similarity is just nothing but the dot product between those two observations. So when we calculated the dot product, we got 64. And in the original dimension, which is like 2D space itself, we calculated the dot product between the points, and we got the same result. In this case, this is the equation of the polynomial kernel, right? Here we set the coefficient of the polynomial as 0, and the degree of the polynomial is set as 2, right? So how do we know C and D? We just have to do cross validation and then tune the values of C and D. That's how you will be able to find out the values of C, and they can be anything, and you will come to know only based on the cross validation that you perform on that particular values. But the base point is the kernel is achieving what the same similarity calculation, even if you're not transforming the point to higher dimensions. So if you come back to this particular equation now, so this is the equation, right? So I set D as 1 by 2 and R as 1 by 2 and D as 2. So I'm expanding this. When I expand this, it is square. I'm writing this as two terms, A into A. So when I calculate, when I do the multiplication, how does that look like? So AB becomes a square plus b square. That is this term, right? So this is what I would like to. So a and a will become a square plus b square, and 1 by 2 into 1 by 2 will be 1 by 4, and the other one, so AB into 1 by 2, 1 by 2 into AB. So we multiply this with this with this. So that becomes AB by 2 plus AB by 2, which becomes AB. So, okay. So when we do this particular, this is a plus b whole square, right? That is nothing but a square plus b square plus 2ab. So 2ab is nothing but 2 into ab into 1 by 2, right? So that becomes ab. So now ab plus a square plus a square b square plus 1 by 4 can be written as the dot product of these two terms, right? So if you calculate the dot product of these two terms, you will get the same result. A into B becomes AB. A next a square into B square becomes A square plus B square. 1 by 2 into 1 by 2 will become 1 by 4. So this is something like a vector in three-dimensional space, right? AI a square z plus 1 by 2 into k. So this is a three-dimensional vector. So this value is your x coordinate, the second one is your y coordinate, and the third one is z coordinate. Okay, so that is how it is written like this. So the other one will become bi plus b square z plus 1 by 2 into k. So when you take the dot product of these two terms, you will I dot product of j will become 0. So these terms will become 0. Only terms that will remain is the first terms, right? I into I will be 1, j into j will be 1, k into k will be 1. That is the reason we are getting the same result, right? So now if you look at this particular point, what does this says? This is nothing but the points in the higher dimensions. The initial points that you have got is a and b, right? A and b are um in which dimension they are in it, they are in one dimensional space. Okay, so as I told you, a and b are in one dimensional space. Now we transform these points in one dimensional space to three-dimensional space. So ab are the points in one dimensional space. To find out the similarity between the points, okay, so why we are transforming the points at the first place? We are transforming the points to higher dimensions because we want to separate the points. In lower dimensions we will not be able to find out a plane that actually separates the classes, but in higher dimensions we would be able to find out that particular hyperplane that separates the points. That is the base idea of these transformations and all these things, right? Now, a point in one-dimensional space A, when this is transformed to three-dimensional space, it is looking something like this: A by A square, A square, 1 by 2. So we are in the first coordinate, we are keeping the same value. In the second coordinate, we are squaring that. In the third dimension, we are making it as a constant value. And the B is moving to B comma B square comma 1 by 2. So any point, if you take any other point, let's suppose these are A and B, right? So if this is C, if you transform this to three-dimensional space, it looks something like that: C square comma 1 by 2. Okay. Now, why we replaced r equal to 1 and d equal to 2? We found out that by cross validation, we found out that in this particular space we are getting higher accuracy. Higher accuracy in the means most of the samples are classified correctly. That's the reason we have set those values. Okay. Now, why we don't here, if you see in the transformation, even though the polynomial column is saying that every point has to be transferred into three-dimensional space, and it also giving us the coordinates in the three-dimensional space, we are not actually moving them to three-dimensional space. If you look at this, we transform these points only into two-dimensional space, which is this is dosage is your x coordinate and the y is dosage square. Okay, if this coordinate x coordinate is called as dosage, y coordinate is nothing but dosage square. Okay, and this is a constant value. As we have a constant value in z axis, so for every point you will have the same x axis, I mean z axis, right? So you can cancel this. as this is just a constant and it is not depending upon the point in the original axis, for every point that the z axis would remain the same. So there is no actual need to project that to z axis. Only projecting that to 2 dimensional would be sufficient, because if you look at this, so this is 2 dimensional space in the now let's transform the points to 2 dimensional space. So every point will be squared, right? Every point would be squared. So this is squared, it goes here. This is squared, it goes here. This is squared, it goes here. And when this is squared, it goes here. When this is squared, this goes here. What does squared means? Let's take an example. If this is 5, so the new this is this point is 5 in x-axis. So the y-axis would become 25. So the point will become 5 comma 25. That is what scaling means. Okay, that is how you're transforming the points. And what happens now, this is on your floor, right? So when you add z-axis, this just floats on your in your 3D space. It just lifts up. So every point will just moves upwards for 1/2 dimensional space, right? For half dimension. So there is no actual need of projecting all the points to z-axis by a constant value. You can just keep them on the y-axis and you can find out that hyperplane. Okay, so to keep it short, when you have the same z-axis, every point, every transformed point will have the same value. So there is no real reason to transform that to z-axis when every point is just moving in the by the same units. So you keep all the points in your 2D space. Okay, now when you transform these points to 2D space, you are able to find out a line that is separating the 2 points. In 1 dimensional space, you cannot find out any hyperplane that separates these 2 points. But when you transform these points to higher dimensional space, you're exactly getting a hyperplane or a line. In 2 dimensional space, it is called as line, and it is able to successfully separate both the points. Okay, so this is called as one of the polynomial kernels, and it based on the degree of your polynomial, it transforms it will do the transformation to the specific number of the dimensions. Okay, so now so these are the high dimensional coordinates. So this is called as polynomial kernel. Okay, now if you go back here, the same thing that I was talking about, right? So we expanded these points and we got the 3 dimensional spaces. So now how does it look like? So this is the x-axis, uh, right? A and B are the x-axis points. A square and B square are the y-axis terms, right? On y-axis, you have to square those 2 points. So A becomes A square, B becomes B square. So the point will move on to 2 dimensional space now. And now the third term is 1/2 and 1/2. But since they are same for both points, we can ignore them. So what happens, the 2 points now, if you consider this as a floor of your room, when the z-axis is set as 1/2 for both the points, they just float on in your room, right? Towards the ceiling. So if this is your room, if you consider this as a room, when you add 1/2, a constant value, they'll just float onto your z-axis. So that doesn't make any difference. Every point will float by the same units. So you don't really need to move them. So whenever there is a constant, there is no actual need to consider those points. Okay. So thus we have x and y axis coordinates for the data in the higher dimension. So as you ignored z axis, even if move the points to x axis, z axis also, you have to find out an hyperplane, but there is no actual need. Okay, but technically this is all conceptual. The kernels will never transform the points to higher dimensional space. That is what kernel trick says. What kernel will do is, in the same dimension, it will try to find out the similarity between the points, and the similarity between the points are used to find out the hyperplane. Okay, thus we have x and y axis coordinates for the data in the higher dimensions. So this is how we will the polynomial kernel with degree 2 is transforming the points to higher dimensions. Okay, in the higher dimensions we are able to find out the line. That is the actual intention of transforming the points to higher dimensional space, because in lower dimensions we were not able to find out the threshold which is separating both the points, but in higher dimensions we are able to find out, a line that separates both the classes so that we would be able to classify the points exactly. Okay. Um, that is about the polynomial kernel, and that is how polynomial kernel actually works um, um, internally. Okay. Now, going back to next slide. So in the earlier case, we got C as 1 by 2 and D as 2. If you have C is equal to, now you have set different values. The coefficient is set to 1 and D is set to 2. The degree of the polynomial is set to 2. When you expand this term, it becomes 2ab plus a square b square plus 1. So that becomes um, root 2a, a square 1, root 2b, b square 1. Okay. So now again, as this is a 2-degree polynomial, you're getting 3 coordinates. Okay. That means you're transforming the points from one-dimensional space to two-dimensional space again, but the z coordinates still have a constant value. So you don't really need to project the point to z axis. So you can just simply ignore them. So the new x-axis will become root 2a. What does that mean? That means that means the new x-axis coordinates are the square root of 2 times the original doses values. So initial points are looking like this. Now the new dimension had become root 2a. So the points will get scaled and moves towards the uh, positive values of x-axis. If you look at this, now the x-axis will move something like this. So this point will become this point will become this. So the points are moving further in the x-axis, right? So the simple example is, if you take any point a as 2, okay, root 2 into 2 will become so before this transformation, if the value of a is equal to 2, okay, so let's suppose if you have one point where a value of a is equal to 2, okay, so let's take an example, let's take a is equal to 2, okay, now root 2a becomes root 2 into 2. So the value of this will be, what is the value of root 2 into 2? Root 2 into,
Somewhere around 2.8.
yeah. So that would be somewhere around 2.8 right now. Sorry. Okay. This would be somewhere around 2.8. That means if the initial point is here, 2. Okay. The initial point is here. Now the new point had become 2.8. So this point has moved forward by 0.8 units. So the new point became 2.8. So this is my new point. Similarly, all other points, if I have multiple points on the same line, okay, I have n number of points on my x-axis, okay, of different classes. So these are of one class, and I do have different points of other class. So now in the transformed space, every point will move forward, this point will move forward, this point will move forward, every point will move towards the higher dimensions of x-axis. So that is what this actual snippet shows us, right? So this snippet shows us that every point that is mentioned, that is placed here, is moving towards the higher dimensional spaces. So if you look at that, this point has moved forward, this point has moved forward, the green point had moved forward. Similarly, every point will move forward on the x-axis. That is what root 2a means. And now the y-axis for the same will become a square. So now these points will move, the y-axis for these points will become a square. That means if a is equal to 2, as I mentioned earlier, if you take an example, if a is equal to 2, the y-axis will become a square. That becomes 2. Let's suppose if a is equal to 2, y is 4. So the point becomes root 2, 2, comma 4. Root 2 into 2, comma 4, which is like 2.8, comma 4. That is how this point, which is 2, will be transformed in the higher dimensional spaces, where you would be able to find out a line that actually separates both the points. Again, the z-axis is 1, so you don't really need to project the points onto z-axis, because every point will move by the same unit, so it doesn't necessarily need to project them. Okay. um, that is what kernel actually will do. What kernel will do is it will just try to transform the points. The kernel trick is nothing but it will do the same action as if they are transformed to the higher dimensional spaces. Okay. um, all right. So now if you take this particular thing, if you take 2 points here, 9 comma 14 are the 2 points here. If you call this point as 9 and this point as 14, you place those 2 points in the polynomial kernel where coefficient is 1 by 2 and degree is 2. And if you solve this equation, you get a value. So this value is nothing but the two-dimensional relationship that we need to solve for the support vector classifier, even though we don't actually transform the data into two-dimensional space. Okay, so we calculated the similarity of these points in the original dimension, in the original space itself, which is 1D space. But this similarity is same as similarity that is calculated in the two-dimensional space, right? If we transform these points to two-dimensional space, if we calculate the similarity in the higher dimensional spaces, the value would also be the same thing, which is 16,002. That is how actually the polynomial kernel work. Is this clear?
Yeah.
Okay. So now moving to the other type of kernel that I was talking about, which is radial basis kernel. So now radial basis kernel try to find out the dimensions, try to find out the similarity in infinite dimensions. Okay. So that is what I'm going to show you how it is going to how it will try to find out the similarity in infinite dimensions. Okay. Um, and let me tell you how does this radial basis kernel actually looks like, and then we will go from there. Uh, just 1 second. So this is how the radial basis RBF kernel looks like. So the polynomial kernel is represented by A cross B plus the coefficient uh, plus coefficient whole to the power of t plus r whole to the power of t. R is the coefficient and d is the degree of the polynomial. And A and B are the 2 points or the two observations. Similarly, the radial basis kernel, which in short is called as RBF kernel, is represented by this formula, whereas it is represented by e to the power of minus gamma to the power of a minus b whole square. Okay, a and b here are just like two measurements or two dosage measurements or two observations or whatever it is. So a and b are the two observations basically. Gamma is uh, gamma is like a constant value which influences this square distance, right? So it scales the square distance. What it is doing, gamma is just like multiplying. It's a constant value, and this just multiplies this particular a minus b whole square, which is the square of the difference between the observations. Okay, it just scales that. So how to actually understand that is, so how does radial kernel basis actually tries to find classify the points is that, um, so this is like, let's come back to how gamma scales this, but let's try to understand how does this actually, you know, uh, it how does this radial basis kernel tries to find out the higher dimensional relationship, which is like infinite dimensional relationship. As I was saying to you, radial basis kernel finds support vector classifier. Support vector classifier is nothing but a hyperplane that separates the two classes, right? It tries to find out that classifier in infinite dimensions. Okay, so it is technically not possible to visualize uh, infinite dimensions. Beyond 3 dimensions, it is tough for us to actually visualize that, but it tries to find out that I can show that mathematically in next few slides. It tries to find out the similarity of the points in infinite dimensions. Okay, by just doing that dot product in the original dimension spaces. It's not dot product, it's just squared sum of the square distances. How does this radial kernel basis actually behaves is that, it behaves like a weighted nearest neighbor model. You have seen that stuff, right? Which is like k nearest neighbors. In k nearest neighbors, what you have done, you have um, assigned the class for the test point based on the nearest points to it, based on the frequency of the class of the points which are close to it, right? That is how you have done it. In other words, the closest observations, also known as the nearest neighbors, have a lot of influence on how we classify the new observations. Okay, so if this is the test point, the nearest points um, to that particular point will determine the class of this point. So in other words, radial basis kernel behaves like an weighted nearest neighbor. So when you get a test point, it tries to the points which are close to it will have more influence on its particular class. As this point is close to the points which are belonging to class red, so this will the test point, which is black color here, will become the will be assigned for the um, patients, or p- to like a patient who is not cured. So basically these points determines, as we discussed earlier, the greens are ones for whom the disease got cured, and the red points are the ones to whom the disease haven't got cured. So if you remember, we were talking about for the patients who were given with the right dosage, the disease got cured. Who were given the low dosage and who were given the high dosage, the disease haven't got cured. But now we got a new patient, and for the new patient, we have given this amount of dosage. Okay, what radial kernel basis will do is, so it tries to find out the points, or in the other words, the points closest to this test point will have more influence on the class to which this will be assigned by the RBF kernel. Okay, that is what it means to say the closest observations have a lot of influence on how we classify the new observation in the weighted nearest model. So radial basis kernel behaves like an weighted nearest neighbor. Okay. Um, all right. Now let's let's come back and look at this. So as I was saying to you, the nearest point will have the highest influence, right? That is what I was trying to convey here. Now, if you take any two observations, okay, if you apply these two observations in the radio kernel basis, let's take gamma is equal to 1 here, and a as if the A is this observation and B is this observation, and we calculate this particular equation with these two observations, we got the value as 0.11. Okay, so we calculated the value of this radial basis kernels, or using these 2 points. This is point 1 and this is point 2. We applied these 2 points into this equation. Okay, so we applied these 2 points in this equation and found out the value became 0.11. Okay, so the similarity in infinite dimensions for these 2 points is 0.11. That is what applying the or substituting the values of a and b into the in this particular radial kernel basis actually defines it. So when you calculate the value of this equation, what that value actually specifies, this value specifies the relationship between these 2 points in or similarity between these 2 points in infinite dimensions, because radial basis kernel tries to find out the similarities in infinite dimensions. Okay, just take this as my word and I'll show you how it actually tries to calculate that similarity in higher dimension in infinite dimension shortly. But similarly, like if you take these two observations and if you calculate the um, RBF kernel's value, it would be very close to 0. Okay, so the higher dimension relationship using RBF kernel for these 2 points is 0, whereas for these 2 points it is 0.11. That says, as this has highest similarity, this will be assigned to this particular point. Okay, numerically that is what it means. So to keep it short, RBF kernel behaves like an weighted nearest neighbor. So the points which are closest to the test point will have more influence on that particular point. That means the class of the nearest points will have more influence to determine the class of that test point. Okay, right. So that is what radial basis kernel basically means. Radial basis kernel will tries to find out the relationship between the observations in infinite dimensions, whereas polynomial kernel is not that is not of that sort. It will not transform the points to infinite dimensions. It just transforms the points to some some sort of like depends on the degree of the polynomial. It would be like 3 dimensions, 6 dimensions, or 12 dimensions, or whatever it is. You can just apply the change that to 3. Like the let's suppose if you take the degree of the polynomial as 1 by 1 whole to the power of 3, apply this and find out it would be somewhere around 6 dimensions. This becomes 6 dimensions. So based on that, the number of dimensions will depend based on the degree of the polynomial. Whereas in radial basis kernel, irrespective of the observations in the dimensions, it will always try to find out the dimensions in the relationships in the infinite dimensions. Okay, do you remember let's go back here as we were talking about that. Do you remember the formula for a plus b whole cube? A plus b whole cube, what is the formula for this? A cube plus b cube plus 3ab into a plus b. Is this right? Right? A cube plus b cube plus 3a square b plus 3ab square. Is this right?
Yes, son.
Ah. So now if you want to convert this into points, if you want to write this as a dot product between these two points, how do you write that? How do you write that? So this has to be converted to this equation, right? So now this is the formula for a plus b whole cube. Now we have to convert this equation to the same thing. So this becomes ab whole cube plus 1 whole cube plus 3 into AB into B is 1 plus A plus B, right? So this becomes AB comma 1, right or not? So we are just applying this A plus B whole cube formula for that. Apart from that, we are not doing anything much here. So now, so when I apply the same formula to these things, so now I'm applying the same formula for this. Now this becomes something like this. So this will be equal to A cube B cube plus 1 plus 3 into AB into AB plus 1. So if I still expand this, this becomes A cube B cube plus 1 plus 3A square B square plus 3AB, right? If I convert this to a dot product, so this becomes A cube root 3A square comma root 3A dot product of B cube comma 1 comma root 3 B square comma root 3B, right? So if I do the dot product of these two things, we will get the same result, because A cube into B cube will become A cube B cube, 1 into 1 will become 1, root 3A square dot product of root 3B square will become 3A square B square, root 3A dot root 3B will become 3AB. That means when you apply the polynomial kernel, degree of the polynomial kernel is 3, you are transforming the points to 4-dimensional space. And uh, if you transform the point to 4-dimensional space and calculate the similarity, if you get the result something like 280, so you don't, without transforming the points to higher dimensions, the same can be achieved just with this formula. So that is how depending on the degree, the dimensions are coming down to. If it is 2, we are transforming the points to 2 dimensions. If it is 3, you're transforming the points to 4-dimensional spaces. But irrespective of there is no such parameter in radial basis kernel. So for every observation, it tries to find out the similarity in infinite dimensions in radial basis kernel. Whereas in polynomial kernel, depending on the degree of the polynomial, it tries to find out the similarity of the points in a specific dimensional set. It can be 4, 6, or 8, depends on the degree of the polynomial. But here there is no such kind of restriction. For every point, for every given point, it tries to find out the higher dimensional relationship. That means it tries to find out the relationship in infinite dimensions. Okay, that is how radial basis kernel actually tries to find out the similarity. In infinite dimensions, as you cannot visualize, to keep it short, radial basis kernel behaves like an weighted nearest neighbor. That means the points which are close to that particular test point will have more influence on the class of uh, influence on uh, the class to which that point will be assigned. Okay, so that is how in short you'll be clarified on how it actually finds out the dimensions in infinite spaces or infinite dimensions. But before that, you just note that this is the formula for radial basis kernel. Radial basis kernel is represented by this equation, and gamma is an constant value which scales the square distance of the observations, and gamma will be determined by cross validation. As I told you, any tuning parameter will always be determined by cross validation in machine learning, right? That is the reason the training of a particular model takes a lot of time, lot of computational capacity, because gamma can take any value. You have to find out the best value that you have to assign to the gamma so that your accuracy of the model is high. Okay, to find out that model, you have to do lots of iterations to get in constant value for gamma. So in determining the gamma, just you can it's just like a common sense. So when the accuracy is decreasing, you go up. When the accuracy is increasing, you go down, something of that sort. Okay, um, uh, that's how you determine the value of gamma, which using cross validation. Now, as I was saying you, gamma scales the square distance between the points. Okay, if you take gamma is equal to 1 for the same 2 points, the similarity is given as, the similarity in infinite dimensions is given as 0.11. When you took gamma is equal to 2, the similarity between these 2 points is given as 0.01 in infinite dimensions. Okay, so that is what actually gamma parameter is. It scales the distance between the points. Apart from that, it doesn't have any much role on this. It just scales the distance between those, scales square distance between the observations. Okay, and now if you apply, as I was saying you, a number very close to zero, right? For these two observations, what does that actually means is like, let's suppose if this point is 2.5 and this point is 16. Okay, so when you calculate the RBF value, or for this, it becomes e to the power of minus 182.25, which is close to zero. Okay, so that is what actually it means is, so between these 2 points, the similarity is is visible, but whereas these 2 points, the similarity is zero. So that is how it tries to find out a hyperplane that separates these 2 points in the same dimensional spaces. So for polynomial kernel, it is again ab plus r whole to the power of t. For radial basis kernel, a to the power of minus gamma a minus b whole square. Radial basis kernel always tries to find out the similarity between the points in infinite dimensions, not like polynomial kernel. Okay, it behaves like weighted nearest neighbors. That means the points which are close to it will have, close to the rest point will have more influence on it when compared to the points which are far away from it. Okay, right. Now let's prove that radial basis kernel calculates the similarity between the points in infinite dimensions. Okay, if you look at the equation of radial basis kernel, it is e to the power of minus gamma a minus b whole square, right? I'm expanding this particular term, which is e to the power of minus gamma a minus b whole square is nothing but a square plus b square minus 2ab. Okay, so I'm again splitting this into two terms, which is e to the power of minus gamma into a square plus b square multiplied by e to the power of gamma 2ab. Okay, so this gamma minus gamma will be multiplied by both these terms. So I am separating this as one term and separating this as another term. Okay, minus and minus will become gamma. Okay, now I got this particular equation, right? Now, e to the power of x can be represented according to Taylor series expansion. I think most of you have seen this in your engineering first year. Using Taylor series expansion, e to the power of x can be represented as 1 plus x by 1 factorial plus x square plus 2 factorial upon x to the power of infinity by infinite factorial. So this is coming from Taylor series expansion. Now, I'm applying the same for this one, e to the power of ab. Let's say gamma is equal to 1. For simplicity, let's say gamma is equal to 1 by 2. Okay, so that this term will become e to the power of ab, right? So gamma is equal to 1 by 2. 1 by 2 into 2 will get cancelled. So that become that comes down to e to the power of ab. Okay, gamma is just a scaling parameter. So you can take anything, any value for that. It basically determined by cross validation, as I was saying to you. So now e to the power of ab can be represented as 1 plus ab by 1 factorial plus ab square, ab whole square by 2 factorial, ab whole ab whole cube by 3 factorial over 1, ab to the ab whole to the power of infinite by infinite factorial. So now if I want to convert this to dot product, what I'll get this thing. So similar to what we have done earlier, this term can be represented as a dot product of these two terms. Okay, 1 into 1 is 1, root of 1 by 1 factorial into a, root of 1 into 1 factorial by a. So root will root 1 by 1 factorial. So this will become the same, right? Root of 1 by 1 factorial. So the root will go away and this turns down to be 1 by 1 factorial. So 1 by 2 factorial is turned down to, so these two terms will become 1 by 2 factorial. A square and b square will become a square b ab whole square. Okay, if you understand that, we are converting e to the power of ab into dot product of 2 points in infinite dimensions, right? So dot product of 2 points in infinite dimensions. That means we transform the point from one-dimensional space to infinite dimensions. And then you're trying to find out the similarity of the points in infinite dimensions, right? So that infinite dimension similarity will be used to find out the um, linear classifier or soft margin classifier, support vector classifier, whatever it is. Okay, so now what is the leftover term for us? Minus, this is the leftover term, right? So I'm just multiplying this. The term gamma is taken as 1 by 2 with the dot product of these two things. So let's call this as S for now. For simplicity, I'm calling this as S. So S multiplied by any of this. So S will be multiplied by every term. Okay. Um, okay. S is taken as root 2. So that means S square is equal to root of 2. So S into S will become S square. Okay. So you can take S square common. S square is nothing but this particular term. So it is just like mathematical, manipulations. That's all we are doing to keep it short. E to the power of anything can be represented in infinite dimensions. That is the reason by default, radial basis kernel is transforming the points to infinite dimensions, and it is trying to find out the similarity between the points in infinite dimensions. Okay. So now if you take any two observations in 2.5 and 4 are one-dimensional observations, right? So when you calculate the RBF value for that, you're getting it as 0.11. What does this 0.11 actually means is that is the similarity between the points in infinite dimensions. The value we get at the end is the relationship between the 2 points in infinite dimensions. So 0.11 is nothing but the value, the similarity between these 2 points in infinite dimensions. Okay. So that is the reason why I'm saying like radial basis kernel will always try to find out the similarity between the points in infinite dimensions. So it tries to find out the similarity in infinite dimensions, and it tries to get that particular value for us. I mean, based on that similarity, it find out the classifier for us. But it's really difficult to imagine that particular stuff but just by how it goes to infinite dimensions, find out the similarity, and how in infinite dimensions it's try to find out that hyperplane that separates those 2 points or those points successfully. We would not be able to visualize that because everything happens in infinite dimensions, and it is difficult for us to represent beyond 3 dimensions on a screen or wherever it is. Even it is difficult to visualize that. So just the mathematical stuff is just proving that, and we have to just believe that. Okay. So radial basis kernel is equal to the dot product that has coordinates for an infinite number of dimensions. Okay. So we are transforming its radial kernel basis nothing but transforming the points to infinite dimensions and finding the similarity between the points. Okay. So this is all about kernels. We started with support vector machines, um, the maths behind support vector machines. We understood what are support vectors, how it actually tries to find out the hyperplane. The points about the hyperplane has h of x greater than 0, less than 0. Just a revision that I want to just quickly do here as we completed this SVM right now. So we started with math with the single line, and we understood the changing how this line moves by changing the values of a, b, c, and by changing the values of a, c, and b. And we found out that any points above the hyperplane will have h of x greater than 0, and for any points below h of x is below that will have h of x less than 0. And then we tried to find out the margin. So when you change the value of um, what is that? Intercept is changing. So when you change the values of c, the line is just moving up and down. So right, slope remains constant, but intercept is changing. And then we found out the lines intercepting the end edges of the clusters are called as support vectors. And then we have seen what is hard margin, soft margin, what is maximum margin classifiers. Um, so what is soft margin we have seen, and then uh, we derived the objective, I mean optimal optimization problem for a support vector machine. We have seen primal formulation of this, and we have from the primal formulation we have solved the dual formulation, and you found out that the Lagrangian multiplier for non-support vectors is 0, and the Lagrangian multiplier for support vector is only greater than 0, is what we have seen. um, and also we have seen how to get the values of W and B, and you also have found out that W weight vector is nothing but the linear combination of all the support vectors. So the non-support vectors has no influence on the hyperplane. Is that what we have seen? We have derived dual formulation. Uh, so we solved this, and then we came back and see what is soft margin SVM, and how does this slack actually helps us to get this constraint satisfied even if we have misclassifications. So that is what we have covered after hard margin SVM classification, and we analyzed how to calculate the slack of a particular variable, and what are the values that are possible for the slack variable. We have seen that, and we also have seen the how this regularization parameter C will have influence on the slack. I mean, on the importance of the slack. We have studied this, and then we introduced the slack into the objective optimal problem, optimization problem, and then using the Lagrangian multipliers, we have solved both primal equation and I mean, with the slack, we solved both primal and dual equations, and the only thing that we have found out is that the value of alpha I is residing between 0 and C. C is the regularization parameter. So with this, the computation will become less. So you doesn't need to find out, go find infinite values for this Lagrangian multiplier, whereas the value of alpha I is just within between, you know, 0 and C. Why we need alpha? To get the weight vector, right? So weight vector can be determined using the alpha I vector. Okay, and then we came with the dual formulation, and this offset B is included within the weight parameter calculations. And then we started kernel SVM. Kernel SVM is basically used to um, find out the separating hyperplane in higher dimensions when we are not able to find out the threshold in the original dimensions. And then I already have shown you what is this kernel. Kernel is, you cannot find out a linear plane for these points here, right? So what you have to do, we were able to find out the separating hyperplane when we transform the points to higher dimensions. Okay, so when we transform the points to higher dimensions, we were able to find out the what is that separating hyperplane. If you look at this, so the two-dimensional spaces are transformed to three-dimensional spaces, and once the points are transformed, we are able to find out the hyperplane that is separating both the points. Okay, that is what transforming the points to higher dimensions, but which is computationally inefficient, and we'll also don't know to how many dimensions we need to transform the points to identify, the relationship between the points. It is technically impossible, but kernels are achieving that using the kernel trick. The uh, the problem is just getting down to choosing one of the few kernels that are available for us. We have linear kernels, polynomial kernel, radial basis kernel, and all stuff. So I explained you the kernel trick here about how the kernels will actually find out the hyperplane. And then we have seen polynomial kernel now and radial basis kernel now. And now the important things that you have to understand is the whole intention of SVM is to find out the hyperplane that separates the points, right? That is the whole intention. Now, when it comes back to primal formulation, in primal formulation, what you're trying to do, you're trying to find out the weight vector. So what are known parameters for you and what are unknown parameters for you? So in primal formulation, the unknown parameters for you is W, B, and I, right? These are the ones that you're trying to find out, the slack W and B. These are unknown parameters. Xi and Yi are the known parameters because you know the points. Yi is the class of a particular point, xi is the given point. Yeah, so you will be given a data matrix. So these are all the futures. These are all the futures, and this is the label, right? This is yi, and this is all this together is called as xi. So you know the data. Xi is also known, y is also known because this is a supervised learning. So you also know the label of a given point. So those are the things that you have. So from this, what you're trying to find out, you're trying to find out weight vector b and slack variable. Okay. So those are the parameters that you're trying to find out in primal formulation. In dual formulation, you know, again, xi and yi, you know, xi and yi are known from the data matrix. And now you also have to use kernel if it is a I mean, if the data is not linearly separable. Okay, using these things, you are aware of these. You're trying to find out alpha I and B. Okay, alpha I determine from alpha I we can get W, and from B will be determined by from one of the support vectors, right? That is those are the known parameters and those are the unknown parameters in support vector machines. Okay. Um, right. I have shown you this, right? So when we differentiate with one of the um, variables, you're getting this as W is equal to alpha I y xi. So you know xi yi, only thing that you have to know is alpha I to get the W. Once you know the W, you can calculate the value of B by using one of the support vectors. So if I remember, I have shown you B is equal to, where is that particular slide? Yeah, here you see, you know ys, you know xs, and you also calculate a w, then you would be able to calculate the b. Okay, so these are the known parameters and unknown parameters in support vector machines. Okay, so this would be a very important question that would be asked in most of the interviews. So that's the reason I have placed here. So you know xi and yi in primal formulation, you know xi, yi and kernel in dual formulation, and then the values that you're trying to find out is WB, sigma n. So dual formulation is computationally effective solution. So whenever you solve SVM, you go with dual formulation, not with the primal formulation. All right. So that is all about different classifiers that we have. Okay. We will come back to other classifiers shortly. We have few more classifiers that we need to discuss. For now, what all we have discussed, we discussed decision trees, we discussed Kernel, naive Bayes, Gaussian naive Bayes, SVM. Any other classifiers that we have discussed? We discussed 5 classifiers, right? We are also going to discuss about rule-based classifiers and also something called as random forests, ADA boost, XG boost, gradient boost. We have to discuss 5 more classifiers. I think, yeah, we are going to cover one classifier, and we need to cover 4 more classifiers in other sessions. But before, we covered most of the classification important classifiers, but it's time to understand few other things. I mean the evaluation the evaluation parameters or of a particular classifier. So now we know how different classifiers are working, and now we want to understand the parameters that are used to measure how the classification is working, or how the classification is actually doing the job done for us, how it is classifying the points. So for understanding which classifier is best suiting our needs, we have few metrics that you have to understand. Okay, so let's dive into that particular stuff of understanding few important concepts which will help us to evaluate the performance of your the performance of the classifiers that we have learned so far. Okay. Okay, now we are going to learn about the confusion matrix. Okay, what is a confusion matrix is? Confusion matrix is a table used to evaluate the performance of a classification model by comparing the predicting and actual outcomes. Okay, so what does this actually means is that confusion matrix is a matrix And this matrix is actually used to evaluate different performance metrics. Okay, so using these values, we will actually calculate different performance metrics of a classifier or a classification model. So this is how the confusion matrix looks like. So on one side you have actual values, and on the other side we have predicted values. Okay, let's suppose you have a classification model. Okay, um, let's um, let's suppose you have 100 emails. Okay, let me explain you what this confusion matrix actually means is. So let's suppose you have 100 emails. Okay, out of this 100 emails, you have 50 emails as spam and 50 emails as not spam. Okay, so this is your data that you have. Okay, now you're trying to, you are using this data to train a specific model. Now you have a model which is trained to predict an email is spam or not. Okay, so let's suppose you can take any model, like you can take decision trees, you can take Kernel, you can take SVM, whatever classifier that is. Okay, you can use any of these classifiers and train a particular model using the data that you do have, and then you are feeding the test data for it. Okay, and you're trying to find out how this model is performing, how accurate this model is performing. You're trying to understand whether this model is rightly classifying the emails which are spam and which are not spam. Okay, now you fed this data, you know the labels of this data. You're using these 100 emails as the test data for to find out the accuracy of this model. And now you also know the labels of these 100 emails. Out of these 100 emails, 50 emails are spam and 50 are not spam. But the model predicted that. What does the model predicted? So the model gave an output that out of these 100 emails, 60 are spam and 40 are not spam. That is what the model gave us output, like model predicted. This is the model prediction. These are the actual results. Now what do you know? You know that actually there are 50 spam and 50 not spam emails. But what does the model has given? Model has given that 60 has predicted that 60 are spam emails and 40 are not spam emails. So this is the predicted. These are predicted values which are predicted by the model, and these are actual values. Now I want to represent these as a single table. So how do I represent this? On one side I'll take the actual values, on the other side I'll take predicted. Okay, now I have spam and no spam, and I have spam as one class and no spam as another class. Now let's understand this particular table clearly. Now let's suppose it said 60 are spam, but out of these 60 emails, only 40 are the real spam emails. Okay, it falsely identified 20 emails which are not spam as spam. You got that? So the model predicted 60 emails as spam, but out of these 60, only 40 are the right predictions. It predicted only 40 emails in the right way, whereas 20 other emails are predicted as wrong. Okay, so out of these 60, as you already have the labels and you also know the emails which are spam, the model is able to identify only 40 emails into the right category, whereas it misclassified 20 emails. Okay, so it predicted 60, right? So the model predicted 60 as spam. Okay, it predicted 60 as spam. How many it predicted? It predicted total 60 as spam. It predicted total 40 as not spam. Out of the 60 which are predicted, How many are actually spam? Only 40 are actually spam and 20 are not spam. So 20 are actually not spam, but model predicted them as spam. You understood? This 20 means model predicted them as spam, but they're actually not spam emails. Okay, they're genuine emails. Understood? So if you look at this particular row, model predicted them as spam and they're spam emails. Understood? Now the model predicted 40 as not spam, right? The model predicted 40 as not spam. But in this 40, 10 are spam emails, which are misclassified by the model, whereas it classified 30 emails correctly, which are not spam. Understood? So I'll place like this: 30 and 10 and 30. So model predicted 10 as not spam, but these 10 are misclassified. They're actually spam emails. Okay. Whereas 30 emails are predicted as not spam. They're actually not spam as well. Understood? That is what confusion matrix is. It is putting down um, the mapping of actual and predicted actually. Are you clear with this?
Yes.
Okay, I'm just trying to repeat this again. So it's simple, but it would look little tricky, but it's simple. So there are 100 emails. Okay, I don't want to go record this before. If you look at this now, let's say spam as positive, because this is a predictor which is trying to find out the spam or not spam. So spam is, let's suppose spam as a positive class and the not spam as negative class. So the first term, this 40, we call that as true positive, means spam correctly classified as spam by the model. So they are called as true positives. They are really spam emails, and the model also predicted them as spam emails. If you look at this term, these are predicted as not spam. Okay, that means not spam is negative. So the model predicted them as not spam, but they are actually spam emails. That means you're falsely placing that into a wrong category. What is that category? That is a negative category. Not spam is a negative category. So false, these are falsely classified by the model. Into which category? Negative category. So these are called as false negatives. These are true positives. These true means rightly done, false means something wrong. So this is rightly predicted by the model. So true. What is the class of it? Positive. So these are true positives. These are false. These are not rightly classified by the model. So false. And to which class it actually predicted? To a negative class. So these are false negatives. So this is also false, predicted as false, but to which category? Positive category. It predicted that as positive. So these are false positives. So this is true negatives. This is true, rightly done. Non-spam emails are rightly identified as not spam. True, as non-spam is negative class. So this is true negatives. Non-spam is a negative. They are rightly identified. So these are true negatives. Okay. So that are the naming conventions of, you know, different columns. I mean, different values in your confusion matrix. Okay. That is what confusion matrix actually is. If you just look at this example below here, so you got this right. So now I just pasted some example here for you to understand. Again, this is an spam, not spam, spam classifier. You have the value is 50. 50 is true positive, means spam correctly classified as spam. False negatives is 10, means spam incorrectly classified as not spam. So these are spam emails. Actually, they are spam, but they're classified as not spam. So false negatives. So these are false positives. They're actually not spam, but predicted as spam. These are true negatives. Not spam emails classified as not spam emails. Okay. False positive is also called as type 1 error. False negative is also called as type 2 error. Okay. And we call this as miss also. This is miss. Okay. The model has to find this as spam, but it missed it. So we call this as type 2 error or miss. Okay. This is called as type 2 error or miss. This is called as type 1 error. Okay. False positives are also called as type 1 error. So that is what confusion matrix actually is. Now this is in here, this is a binary classifier, right? Why this is a binary classifier? Because you have only two classes, whereas your model is trying to just find out whether it is spam or not spam. That is 1 or 0. Okay, such kind of classifiers are called as binary classifiers. But when you have multi-class classifiers, let's suppose you're trying to find out, classify three different animals, like you're trying to find out, classify dog, cat and rat. Okay, when you're trying to these classify into one of these classes, this is called as multi-class classifier. More than two classes called as binary classifier. More than two classes is called as multi-class classifier. So when you feed an image to a particular model, it has to find out one of these two images. So it has to tag this image to one of these classes. So as you have more than two classes, such kind of classes are called as multi-class classifiers. And how does confusion matrix actually looks for the multi-class classifiers is something like this. Okay. So for multi-class classifiers, the confusion matrix looks like this. So it would be a 3 by 3 matrix. So for binary class classification, it is a 2 by 2 matrix because you have two classes. One is spam, non-spam, spam, non-spam. Whereas when you have more than two classes, it would be 3 by 3. Here you have three classes, so it would be 3 by 3 matrix. And if you have n classes, it would be n by n matrix. Okay, the confusion matrix is just like an square matrix with dimension as number of classes. Now let's look at different terminologies in the multi-class classifier. So how do we call this? This is correct predictions, right? So actual class is A, the predicted class is A. So these are all true positives of class A. These are true positives of class B. These are true positives of class C. Whereas the class B and C items are predicted as A. So these are false positives. Okay. That means how do we read BA? Okay. Actually, class B instance incorrectly predicted as class A. So class B is incorrectly predicted as class A. Class C is incorrectly predicted as class A. Okay. Even if you look at this, class A incorrectly predicted as class B. Class C incorrectly predicted as class B. Okay. So this is how the confusion matrix looks like for a multi-class classifier. Okay. So this is an example. Let's suppose if you have three classes as diabetics, hypertension, and cardiovascular diseases. So 40 patients who has diabetes are correctly identified as diabetic patients, but these 7 patients are incorrectly predicted as diabetes, right? 4 patients who has hypertension are identified as diabetic patients. 3 patients who has heart diseases are identified as diabetic patients. So here the model failed to classify them into a right category or to a right class. Okay, so this is also a failure. So a patient who has diabetes is identified or predicted as a patient with hypertension. A patient with cardiovascular disease is identified as a patient with hypertension. Okay, so this is how the confusion matrix looks like for an multi-class classifier. Is this clear? Understood? Because
Yes.
constructing confusion matrix is very important because every every performance matrix is calculated using the confusion matrix only. You will shortly see all of them now. Okay. Now, key metrics from the now using that confusion matrix, we calculate different values or different performance metrics. Okay. How do we calculate different performance metrics is what we will understand now. Right. So the first one is accuracy. You already have heard about accuracy. What is the formula for accuracy that we have seen before? What is the formula for accuracy? How do we calculate the accuracy of a particular model? Do you remember accuracy is nothing but number of correct predictions by total number of predictions? How do you say the accuracy of a model? Let's suppose you trained a model. Let's suppose you trained a model. Okay. Let's suppose you trained a model and you have your test data. Okay. Um, so let's suppose you have 1,000 records or 1,000 points in your data set. Out of these 1,000 points, you used 800 points to train the model and you have used 200 points. I mean, 200 points as test data set. Now, once you train the model using these 800 points, you test the model using these 200 points, right? So now how does this model is predicting this, the classes of these 200 models is what accuracy basically tells you. So out of these 200, it correctly identified 100 points. Okay. That means out of 200, it correctly classified 100 points. So the accuracy would become it correctly identified 100 points out of 200. So this is what the accuracy is. Okay. Let's suppose it just identified only 10 points correctly, or it classified only 10 points into the right class. So the accuracy will becomes 10 by 200. So out of 200 points, it correctly predicted only 10 points as a into the right class. Whereas it for 190 points, it didn't classify them to a right class. So the accuracy of this is higher than this particular model. Okay. So let's suppose this is the model one that is trained. This is model two. So the accuracy of the model two is greater than accuracy of the model one. Okay. So that is what accuracy is. Now, if you want to convert that accuracy, which is like total number of right predictions by total number of predictions, by using the confusion matrix, it can be written using like this. Okay. If I go back here, so now accuracy, we already know total number of right predictions by total number of predictions. In the confusion matrix, what are the right predictions? This is right prediction, this is right prediction, right? So the positives are the actual is positive and also predicted is positive. So this is the right predictions done by the model, and the negatives are identified as negatives. So these are the right ones. So on the numerator, TP plus TN, the right predictions by total number of predictions is nothing but the sum of all the values in this confusion matrix. So these are wrongly identified, these are wrongly identified. So the sum of all of them will be equal to the total observations. So that is what accuracy is. Precision. Are you able to follow me, or any questions, or you're not following? You want to view this later? Where are we? Hello.
Yeah.
Now we are going to study about this precision and recall. Okay. Now let's understand what are precision and what is recall, and why do we need to have these many number of metrics to evaluate the performance of model. Why not only accuracy is sufficient? Why we need another parameters like precision, recall, and all those things? Can't accuracy be applied for every model? Can't we just rely on how many right predictions done by the model by to the total number of observations that we have given to the model for the prediction? is what we will see. The two things that we find out is why we need so many number of you know evaluation parameters or evaluation metrics. Can't accuracy alone can suffice to say whether the model is right model or not. All right, so we will understand all that stuff. Precision means positive prediction value. What precision says is that out of all the predictions that the model has made, how many are actually correct? Okay, if you look at the formula for precision, it is given as TP by TP plus FP. So this TP plus FP is nothing but the total number of predictions predicted as positive by the model, right? So TP plus FP is nothing but these are the total number of predictions predicted by the model as positive. Let's suppose if the positive class is spam, the total number of emails classified as spam by the model. Okay, so that is what. So TP plus FP is the total number of observations classified as positive by the model. But out of these observations or predictions, how many are right? How many are rightly predicted as positive and how many are not rightly classified as positive? So out of TP plus FP, only TP number of observations are rightly classified or are the actual positives. Okay, so the formula for prediction precision is that out of the total number of positive predictions made by the model, how many are actual positives? Okay, so that is what precision says. The precision is the ratio of correctly predicted positive observations to the total predicted positive observations. Correctly predicted positive observations to the total predicted positive observations. Okay, so TP by TP plus FP, that is what precision actually means is. Okay, precision measures how many positive predictions made by the model are actually correct, whereas the other parameter is recall. Okay, this is positive predicted value. Recall is also called as sensitivity or true positive rate. Okay. Sensitivity. Recall is also called as sensitivity or true positive rate. What recall says is out of the total actual positive values, how many are correctly predicted? Okay. How many, the ratio of correctly predicted positive observations to the actual positives. Correctly predicted positive observations to the actual positives. So actual positives is nothing but TP plus Fn, right? So total actual positives is TP plus Fn. Out of the total actual positives, how many are correctly classified or how many are correctly predicted? Out of TP plus Sn, only TP number of observations are correctly classified as positives. Okay, that is what recall is. Okay, precision is out of all the positive predicted, out of all the positives predicted by the model, how many are rightly classified or rightly predicted? How many positives are, or how many are the actual positives out of all the positives predicted? That is TP by TP plus FP. So out of all the predicted positives, how many are correctly predicted or how many are rightly classified? Whereas recall is out of all the actual positives, how many are actually identified as the or how many are rightly classified out of all actual positives, how many are correctly classified? Okay, so that is TP by TP plus Fn, TP by TP plus FP, TP by TP plus Fn. So that is what recall and precision formulas are. Okay, that is what precision and recall is. Now understand this is very important thing that you have to understand that helps you, and like what has to be given preference and what not. Okay, when to give preference for precision, when you want to have high recall. Okay, that's what you have to understand. Now you know what is precision and what is recall. The precision is how many of the predicted positives are actually positives, and the recall is how many of the how many observations are rightly classified as positives out of all the actual positives. Okay, so that is what precision and recall is. Now You have to understand when to prefer highest precision over recall. When to prefer highest recall over precision. Okay, we will understand that shortly. Okay, so there is something called as precision and recall trade-off. Okay, you cannot have both precision and recall high. Okay, if you increase precision, it will reduce recall, and vice versa. This is called as precision recall trade-off. So precision, if you look at this graph, precision recall graph, the red one is the precision and the blue one is the recall. If you look at this, when precision is low, recall is high. When the recall is low, precision is high. They are actually joining at one point. Okay. In some space, they are close to each other, but when the, when we are putting, when we are going away, something called as, we call as threshold scale, when the threshold is low or high, the difference between the precision and the recall is growing. So unfortunately, you cannot have both precision and recall as high. Okay. When precision is high, recall will be low, and when recall is high, precision is low. This is called as precision and recall trade-off. Now you have to decide whether you want to have high precision or high recall. That is what you have to decide. And I'll give you I'll give you some examples to understand when to use high precision and when to use high recall. Okay, that it all comes down to, let's suppose you learned about 5 different classifiers now, right? Decision trees, KNN, um, whatever, naive Bayes and all that stuff. So let's suppose your you want to have you want to find out a classifier, or you want to use a classifier where the precision is high, and recall is low. Okay, so that is how your model has to behave. So how to actually, in which cases you want to have high precision and in which cases you want to have low recall, we will shortly study that, but let's understand this. So your criteria is that you want to find out, and you want to use a classifier or found out a classifier out of all the classifiers that are available for you, such that the classifier is giving you high precision, okay, and low recall. Let's suppose if you have this classifier one, you sent your test data for this, or you fed your test data for that, and it came up with some results. And when you calculated the results of this model, it is giving high recall. Okay, this is giving high recall. This is giving high recall. This is giving high precision. This is giving high precision. This is giving medium precision and medium recall. Then what you will go with? You will go with this particular classifier for that particular scenario, right? That is how you decide the classifier based on the performance metrics, and you have to decide what is the performance metrics that you want to achieve, whether you want high accuracy, high recall, or high precision. That is something that you have to decide. Okay, the choice between prioritizing high precision and high recall depends on the context and the cost of false positives, incorrectly predicting a positive versus false negatives, incorrectly predicting a negative. Okay, the choice between prioritizing high precision and high recall depends on the context. So you have to decide based on your scenario, you have to decide whether you want high precision or high recall. Okay, let's go back to the next slide to understand this stuff. Cost of false positives versus false negatives. If I go back to the next slide, and you see some scenarios here. Okay, let's see, where do you want high precision and where do you want high recall? Let's understand with some examples. Okay, so high precision, you know what is the precision? Precision is true positive by true positive plus for false positives, right? So this is your confusion matrix. This is true positives. This is false positives. These are false negatives. These are true negatives. Precision always concentrates on this particular row, right? Precision's focus is just this row. It tries to find out when your scenario says you want to have high precision, that means TP by TP plus FP is something that is called as precision. So for precision to be high, FP has to be 0. Then precision is equal to 1, right? When FP is equal to 0, when FP is equal to 0, okay, precision is equal to 1. The precision is high. So what is FP equal to 0 means? What is FP is equal to 0 means? That means out of all the observations or out of all the positive predictions made by the classifier, everything is right. Okay. That is called cost of false positives. If you look at this, incorrectly predicting a positive. So if you predict something which is positive, okay, incorrectly predicting positive. So the FP is nothing but you're predicting something as positive, which is not right, right? So you're predicting something as positive, but actually this is not positive. What is the cost of that? Okay, let's understand this example. You have emails, right? You have spam emails and not spam emails. Let's take this case. You're talking about spam and not spam again. This is spam and not spam. Okay. Now the focus is this is actual spam and this is not spam. So these are actuals. And if you understand that you predicted some, let's suppose FP is equal to 1. Okay. That means you predicted one email as spam, but this email is not spam. Understood? So what is the cost of that? So basically you never go to spam folder, right? You never view spam emails, but you got an offer letter and your predictor classified that as spam and it moved that email to your spam folder, and you will never know that you got an offer letter. So it is a high cost, right? In that case, what should you choose? You have to choose the precision to be high such that out of the predicted positives, it will never, I mean, it will never try to move the items to spam folder. In worst case, it predicts everything as not spam. Okay. Are you understanding that? So the cost of moving a genuine email to spam is high. You don't want to move not spam emails to spam emails. It is okay to move spam emails to inbox. Okay, it's okay to have some spam emails in your inbox, but it is not okay to move right emails to spam folder. In such cases, the precision has to be high. You want to decrease the cost of false positive is high in that case. You are getting that? It is okay. So this is not spam. You don't really bother about them because when the predictor identifies something as not spam, they will be in inbox. Your concern is only with spam, and out of spam your concern is only with false positives, because if it is really spam, moving that to spam folder doesn't has any harm. But if you are moving a genuine email to which is false positive, you are moving a genuine email to spam folder, this is costly. You don't want to do that. Okay. So all of this, when the model predicted an email as not spam, all of these emails will be in your inbox. And if this is actual spam, it is okay to be in spam, but your concentration is here. FP has to be low because you don't want any genuine emails to be in the spam folder. Okay. So in that cases, you have to make sure you want to have high precision. Understood? It is critical to minimize the false positives. You don't want right emails to be in the spam folder. You want to choose a classifier such that the false positives or false positive should be no, right? It's almost equal to 0. So this email classification is an example. Ensuring the genuine emails are not mistakenly classified as spam. Let's suppose if you're getting an offer letter or if you're getting a business communication, and if this classifier predicted that as a spam, it goes to spam and you lost some communication, right? So that is not what you need. Okay. So in such cases, you need high precision. Okay. Um, why precision matters here? Because if important emails are classified as spam, false positives, the user might miss essential communications. It is better to have some spam in the inbox. It is okay to have some spam in the inbox. Okay. Let's suppose if you look at this, these are identified as not spam, but they're actually spam emails, right? This FN is actually spam emails, but they're identified as not spam. That's okay if you have some emails in your inbox. That is totally fine, acceptable. But if you have some spam emails, if you have some genuine emails or not spam emails are predicted as spam, you lose some communication. So in such cases, you have to go with high precision. Okay. If you take another example, goal, recommended product that users is likely to purchase. Okay. So you see recommended products on Amazon. If you're doing like recommending irrelevant products, false positives. Okay. So these products are something which the user don't wants to see. Okay. These are irrelevant. If you take this class, irrelevant products, um, recommended products. It's okay to have, you know, uh, these. Let me just clear this so that you'll understand. Have you got some understanding on in which cases you want to have high precision? So the email is easy to understand actually. Okay, if you take the other example, let's take not recommended, recommended products, not recommended, recommended products. Let's take the vice versa, so it would be easy. So I'll take this in the other way. So I'll take the recommended as positive and not recommended as negative classes. Okay, because it's a recommended system, right? Okay, so this is recommended and this is not recommended. This is recommended and this is not recommended. Now, again, here in this case, you want to have high precision because you don't want, these are actually, this is predicted, right? You don't want to, when the model predicted these false positives as recommended, but the user don't want, the actual is not recommended. User don't want to see these products. But if you still show them as recommended, it actually irritates them. Okay. Let's suppose some of them don't actually want to see some products in their product list. Okay. So you know, the items that females use are irrelevant to male user. So if you show only female products to a male user, it actually gives him some wrong impression on the product, on the application itself, right? So when you recommend not recommended products to an user, it actually creates lots of negative impact on it, negative impact on the user. So not recommended is anyways not a concern because you're not recommending these products to the user. What are the products only recommending? You're recommending only the products in this row, right? So these are the products that you're recommending. Out of these products that you're recommending, it is okay to, and these are all what user wants to see. If you have some items in this row, these are what user wants to see these items. That is okay, you recommend them, but user don't wants to see these records, but you still recommending them to the user. So in this case, you want to nullify this. You want to make this as 0. So in such cases, you want to choose high precision. So in such kinds of cases, you want to have your system to have high precision. So that is what precision and recall trade-off is. In which cases, in which business cases you want to have high recall and in which cases you want to have high precision. Now you understand in which cases you want to have high precision. The examples is product recommendation system. So when the model predicted something as not recommended, anyways, this will not be coming up in the user's catalog. So you don't bother about them. You only bother about the predictions or the recommended products. So these are the products that comes onto the catalog of the user. Let's suppose the if it is 3 and if it is 100, this will negate. Let's suppose 100 are predicted as recommended, but actually they are not recommended. So these are only 3 products which are recommended are predicted as recommended. So in this case, if you have a user page, out of you are displaying him 103 items, out of 103 you are recommending 100 irrelevant items, not recommended items for that user. That actually irritates the user. So the ideal case is you want to make the not recommended as low as possible, or what, you in the ideal case you want to make it as 0, right? So precision is nothing but true positive by true positive plus false positive. You want to make it as low, or in the best case you want to make it as 0. When fp is high, when fp is high when it is more than tp, and fp is more than tp, you're actually messing up the system. Okay, the prediction algorithm itself is messing up the whole application. So in that case, what you're doing what the user don't want to see. Okay, so such classifiers, in such cases you want to have the precision high. Precision high means you're trying to minimize this particular row. Understood? In which cases you want to have high precision.
Yes. Yes.
Now, you want to see in which cases, in which business cases you want to have high recall. You understood when to have high precision, and now it's time to understand when to have high recall. So that is what it basically means is, so it's user decision, or the develop or the ML engineer's decision to choose high recall or high precision. Okay, now let's understand what is recall. Recall is nothing but out of total actuals. Out of total actuals means true positives plus false negatives. Out of total actuals, how many are rightly classified? Okay, how many are actual positives? How many predicted are actual? So again, if you go back to the particular confusion matrix again, now what you're trying to minimize? You're trying to minimize, in this case, your actual concentration is on which row? Again, so these are actuals, these are predicteds. Okay,
Actual positive.
now when you want to have high recall, what do you want to have? You have f1 is equal to 0, right? That means your concentration is on this row. On which row? Your concentration is on this particular section. You don't bother about this row at all now. Okay, you don't bother about this row at all. In this row, only the row that matters to you is this row. Okay, in this row, your main concentration is make sure this row has very less value or equal to 0. Okay, when fn is equal to 0, recall will be equal to 1, because recall is nothing but tp by tp plus fn. Now let's understand uh, the the use case where you want to have high recall. Okay, so these are actuals. Okay, now identify as many cases. Let's suppose this is the case: disease screening program, infectious disease. If that is an infectious disease like corona or something. Okay, so corona or something. Okay, now in the cases of corona, what do you want to what do you want to find out? You want to find out the patients who got infected at an early stage, right? It is okay even if you identified someone who don't have corona as a corona patient, but if you missed identifying a patient with corona as a patient who, as a patient with who has not got infected with corona, he will go out roam freely, and he will spread the disease faster, right? So are you understanding this? So if you take the example of corona, it is okay to identify a patient um, who has who was not infected with corona as someone who got infected with corona. That is fine, because you will place them in quarantine, and he will just stay in that particular quarantine um, facility. But if you leave someone who has corona as, or if you predict someone who has corona as someone who is not infected with corona, you will leave him from the quarantine area and he will just go and spread that disease to so many people. In that case, what is more important? Let's suppose predicted as corona and not corona, as corona infected and not corona infected. So if you predict someone as infected as corona, even if it has no corona, it is not an issue, right? But if you find if you so this is not an issue. Do you agree with me? So this is not an issue because you are trying to
Yes.
predict these patients as having as infected with corona, but actually they are not infected, but you identified them as corona infected patients. Then what you will do, you keep them in quarantine region and everything is safe. But this population I'm talking about, so when you are predicting these patients as not have are not infected with corona, even though they have corona, what happens? They will just go and spread the disease, right? So in such cases, when you're trying to uh, develop a classifier for such kinds of for such kind of situations, what is your main intention? You want to minimize this. You want to leave only basically you don't want to leave any patient who got infected with corona, right? You don't want to misclassify any of the infected patients. Okay, ideally you want to make it as zero, but if even if it has very less value, when false negatives is much less than TP, that is fine, that is acceptable. But when false negative is greater than TP, what happens? Many patients are wrongly classified. When they have corona, they were misclassified as patients with not corona. They will just go out, spread the disease much faster, right? So in such cases, this false positives are not an issue. Even if you predict someone with corona as with not corona as corona, you will keep them as quarantine and you will take care of them. You will just go with for further test and you will find out that. But if you leave someone with corona outside, it's an issue. So in such kinds of cases, you want to have high recall. Understood? You understood when to have high recall and when to have high precision?
High precision have FP is low.
Hmm.
High recall FN is low.
Yeah, so that F1 and FE, yeah, you have to understand the business cases, but in future you will get a case, you'll get a business condition. So what do you want to, what do you have to decide whether you want to have high recall or high precision. Okay, so that is in some cases you want to have you don't have any specific choice, then you will understand. Then we will come to that shortly, but at this point of time, I want to understand when to choose the business cases or the cases where you want to have high precision and high recall. So that's an a good example, I think. So missing a disease case, false negative means a patient doesn't receive timely treatment, which could lead to worse health conditions or increase the spread of contagious diseases. High recall ensures more potential cases are detected for further testing, even if some false positives occur. So false positives is not a concern. Okay. So security and intrusion detection. Detect all positive threats on or intrusion in a network. So even if you identify some intrusion into your network, even that is not an threat, that is fine. But if you miss something, a potential intrusion or potential hacking, if you miss such kind of potential hacking, they will actually seize all your systems, right? So false positive threats or intrusions into your network. So in such cases, you want to have high precision. You don't want, even if you identified intrusions which are not actually hackings, that is okay to identify them as intrusions. But if you miss some valid intrusion as not an as not a threat, yeah, that is an issue. So that is an example of having high recall. Okay. These are just examples I want to show you because you want to understand when to choose high recall and when to choose high precision. High recall and precision will not happen at the same time. When recall is high, precision will be low, and when precision is low, recall will be high. From this graph, you understand that's why we have precision and recall trade-off. So you have to choose the trade-off. You have to choose whether you want to have high precision in that case or high recall in this case. Okay. So those are the cases. Now let's calculate how do we achieve that. Okay. How do we achieve that is something. Let's suppose you are now we are saying you want to have high precision but low recall. How to design your system? You never have seen having high precision and high recall before, right? Let me just give you a simple example here and then you will understand clearly. Okay. So I'll walk you through this application and then I think you will be understand how to choose, how to achieve that. Now you understand what you want to achieve. Let's suppose you understand whether you want high precision or high recall, right? But now you want to understand now. Let me walk you through like how to achieve high precision and high recall. So you have seen naive-Bayes classifier, right? You have seen naive-Bayes classifier, and we also have done an example. But how to introduce, precision and recall to that? Okay, let me explain this to you. So now this is your case. You understood naive-Bayes classifier. What does naive-Bayes classifier will do is so naive-Bayes classifier will try to find out the probability of spam given an email, right? Given an email. And it also tries to find out the probability of not a spam given an email. Okay. You in naive Bayes, you will try to, if it is a continuous, if it is a regression case, this is a classification case. And if you have a regression case, you will go with naive Bayes classifier. We already have studied that. Now in naive Bayes, what you will find out this posterior probabilities, right? Using the prior probabilities and likelihoods. Okay, using the Bayes theorem. So you will find out the probability of spam given an email and the probability of not spam given an email. And when you find whichever has highest probability, you will assign that email to that particular class. Let's suppose the probability of this is 0.65 and the probability of this is 0.5. As probability of spam given email is greater than probability of not spam given an email, you're assigning this email as spam email. So this is what naive Bayes classifier will do is, right? Right or not? Do you remember this?
It's Bayes theorem.
Yeah, naive Bayes theorem. Now, along with this condition, I'm also adding a new condition. Okay. What is that condition? So when probability of spam given an email is greater than probability of not spam given an email and probability of spam given an email should also be greater than 0.9, then only if this condition is satisfied, then only assign that email as spam. Okay. Now come back to the same example. Now 0.65 is greater than 0.5 and 0.65 is greater than 0.9. Okay. This is true. This is true. This is false. Okay. True and false is false. So this will be assigned as not spam, right? When you have only this condition, we are marking that as spam. But you introduced another condition, which is called as threshold. This is called as threshold. Only even if the other condition is met, only if this threshold is reached, then only you will classify that as a spam. In that case, what you are increasing. So if you look at these values, they are very close, right? You cannot say that with high confidence. There is a lot of chance that it can also be a not spam. right? And even if the probability of the spam is higher, but the difference is very low, so there is a high probability that it is also not spam email. So we don't want to take that risk. We want to classify. This is like achieving high precision, right? This is like achieving high precision, because in high precision, what you don't want to do, you don't want to assign, you want to reduce false positive. That means you don't want to assign, or you don't want to predict in not spam email as spam, right? So that's why you're increasing the threshold. You want to make sure only the probability is greater than 0.9. Means the probability is greater than 0.9 means it should be greater than 90% confidence. It should have more than 90% confidence. Then only you're classifying that as spam, even though this condition is achieved. If you look at these probabilities, they are very close. You cannot actually confidently say that is spam email. But according to naive Bayes, as this condition is met, you're just assigning that to spam. So this could be false prediction. Okay, there is high chances that this is a false prediction, but you don't want to take that risk. So to avoid that risk, what you're doing, you're also adding another threshold. Understood? Using this threshold, what you're doing, you're achieving the precision. So until unless you are very confident, very high confident with being that as a spam, you're not assigning that as a spam. You're simply assigning that to not spam. So in worst case, you're assigning everything as not spam. Okay. That means you're considering in worst case, you're assigning everything that as a not spam. That means you're showing every spam email in your inbox. Okay. So that is what threshold is. That is how you achieve high precision or high recall. Understood? How do you achieve recall? Recall is nothing but the opposite to this. The not spam should be greater than 0.9. Understood? All right. Now this is how you achieve high recalls and high precisions by adding just threshold or modify the algorithm a bit by getting the output of it or the probabilities of that. Okay. Now let me show you this example of calculating. Now, as I told you, let me show you this example, then you will clearly understand how does this precision is actually varying. Okay. Let me give you this example. Now, let's suppose I have 10 emails. Okay. I have how many emails? 10 emails. And I'm calculating the probability of spam given an email. So these are all the probabilities of spam given an email. Okay. These are all probabilities of spam given an email. These are all probabilities of spam given an email. Okay. So 0.95, 0.9, 0.8, 0.7, these are all probabilities of different emails given, probabilities of spam given an emails. Now these are the actual labels. Actual labels. These are actual labels. That means this is a spam email, this is a spam, this is a spam email, this is a spam email, this is a spam email, and the rest all are not spam emails. Now I set the threshold here. I will classify an email as spam only if probability of spam given an email is greater than 0.95. You understood that? When the probability of spam given an email is greater than 0.95, then only I'll classify that as spam, or else I'll classify that as not spam. Okay. Now, if I have this threshold here, okay, let's put the values of the confusion matrix in this. Now, when the threshold is here, I will classify only one email as spam and 9 emails as not spams, right? Because only for one email out of the 10 samples that are given to us, only one email has threshold greater than 0.95. So my classifier will classify only one email as spam and 9 as not spam. Now, if you fill this table. So out of how many total spams that you do have? You have 5 total spam emails. These are predicted for that threshold. The actual is 5 spams, 5 not spams. Okay. Out of 5, only one spam is predicted. It predicted one spam, right? Correctly. The total predictions that it made is one spams. So the NS is 0. So the total spam predictions made by the classifier is only 1. The total non-spam predictions made is 9. Out of 9, how many actual non-spam emails? 5 are non-spam emails. But others are 4. So it predicted 4 emails as not spam, but they're actually spam emails. Understood? Understood how we came up with these values? Yes or no?
Yes.
Okay. Now, let's say this is my threshold now. Okay, this is my threshold now. Tell me what are the values in this table? What will be the values in this table? What will be the predicteds if this is the threshold, and what will be the actuals if this is the threshold? Actuals will always be 5 spam and 5 not spam. Okay, what will
Issued
be the
value.
predict?
Issued value what?
What?
Issued value 0.95 for all.
0 point?
Issued value is same for all or not? I asking.
Which value?
0.7. You asking?
Yeah, that is the new threshold. 0.7 is my
Yes.
new threshold. I was explaining you, right? So threshold is nothing but the additional parameter that I have added. So only when the probability of spam given in email is greater than 0.7 or greater than or equal to 0.7, then only I'll classify that as a spam email, or else I'll classify that as not spam emails, not spam. So out of 10, how many will be
Same as upper table.
same? So
Same
for
as upper table.
how?
If threshold as 0.7 greater than, is there only one success, one spam is there.
So now probability of spam given an email is greater than 0.7, right? So 0.8 is
Yeah.
greater than 0.7, 0.9 is greater than 0.7, 0.95 is
Our,
greater than 0.7, right? So all of them will be
yeah.
classified as spam emails, right?
Yes. We have
So now
four,
how many will be predicted as spam now? And how many will be predicted as not
four,
spam?
four.
Four will be predicted as spam. How many
Spam.
will be predicted as not spam?
6.
6 will be predicted as not spam. Then how, if you fill this table, how does this look like? So the total spams predicted is 4. The total
4.
non-spam predicted is 6.
6.
So out of 4 predicted, 4 are spam. Okay.
Non-spam 0.
Non-spam 0. So out of 6 predicted, 5 out of 6 non-spam predicted, 5 are
5.
spam.
No, as 1.
This is 1. Okay.
Yeah. Yeah.
Now if you take this as a threshold, what are the values for this? Again, you have to write predicted, actual.
6.
Actual will always be 5s,
5.
5 spam.
5.
So what will be the predicted spam here?
6.
6 predicted spam. And how many are not non-spams?
4.
4 non-spams. So how does this table look like now?
6. 0.
6 0.
We have 4 only. 4. 0. 4.
0 4. Where is 0 4?
SNS 0. NSNS 4.
What is that? What will come here? So the total predicted spams are
6.
6.
6. 6.
Predicted non-spams are 4. So
4.
out of the 6, 5 are actual spams. So 1 is not spam. So it predicted 6 emails as not spams, right? So
Non-spam.
these are the 6 emails it has predicted as spam. These are the 6 emails it predicted as spam. Out of them, 5 are actual spams, but 1 is not spam. So out of 6 predictions that it has made, one is not spam, right? This particular email is misclassified. This is not spam, but it predicted that as spam, right? So now out of these 4, this is 4 and this is 0,
4 and 0.
right? Okay. Now if the threshold is this, if the threshold is this, how does that look like? So we filled all the tables. Now we are left with only one threshold, which is this. Okay, let's fill this table and then you can calculate you know the precision and recall for all the confusion matrix. Okay, now tell me this table now. How, if the threshold is here, what will be the values here? What are the predicteds? What are the actuals? Actuals is always 5 spam, 5 not spam. So what are the predicteds now here?
5401.
This is 5, 4,
4
0,
0 1.
right? Because
1.
9 are as spam,
Success.
1 as not spam.
1 at non-spam.
So out of 9, 5 are right spam emails.
Spams.
4 are predicted as spam, but they are not spam. Okay, these are false positives. So none of them are predicted as not spam, which are spam.
Non-spam.
So this will be 0, this will be 1, right? Awesome. Now calculate the precision and recall for all of these tables. Okay. You can do the calculations and let me know the values. Meanwhile, I'll just try to just write precision and recall everywhere. Calculate the precision and recall for every table, this is a confusion matrix, right? Now let's calculate the precision and recall for every confusion matrix placed over here. Just erasing these things. Okay, right. I'm trying to calculate the precision is called as recall here. Precision for this table, recall for this table. Precision for this table, recall for this table. Precision for this table, recall for this table. Okay, what is the precision for this table?
1.
What is the recall?
Recall 0.2.
0.2, awesome. Let me just ask others. I don't know whether they are understanding this or not. Who are there? Ashwant, Valli, Madhu. Can someone tell me what is the precision and recall for this particular table?
Precision 1.
Precision 1,
Recall would be 4 by 5. 0.8.
0.8.
Yes.
Okay, what is the precision and recall for this? Madhu, Valli. Precision for this. What is the precision for this? 5 by 6, right?
Yeah.
What is the value of
0.8. 0.83.
Okay, 0. Right, 0.8 something around. What is the recall?
1.
Okay. What is the precision recall for the other table?
0.5.
0.5.
Yeah.
0.5. 5 by 9, right?
Yes.
Okay.
1. Precision is 1.
Now I'll place the precision recall side by side here. So the precision is 1 comma 0.2. This is precision and recall. And here it is 1 comma 0.8. Precision and recall. Here it is 0.8 comma 1. This is precision and recall. and here it is 0.5 comma 1, precision and recall. Okay, so if you carefully look at this, so when the threshold is kept above, so I'm just erasing everything. So if you look at this, here the precision is 1 and the recall is low. When the threshold is high, okay, when the threshold is high, precision is high, recall is low. When we move down, precision is decreasing and recall is increasing, right? The precision recall is 0.2, 0.811. Recall is increasing when the threshold is coming down. And when the threshold is increased, precision is increasing. Okay. So when precision is high, recall is low. When precision is low, recall is high. When the threshold is in between, they both are little close to each other. Now you understand this, right? You understood this?
Yes.
Okay. Now let me just go back to that graph which I was showing earlier. So now it makes sense to you. If I go back to the previous slides, now if you look at this, when the threshold is set to low values, recall is high. Okay. When the threshold is reaching high, the precision is high. You're seeing this? When the threshold is very high value, the precision is high, recall is very low. When it is in between the high and lows, recall and precisions are somewhere around equal. Okay. But when we are setting the threshold to very low value, in that case, recall is high, precision is low. Now this graph makes sense to you? Hello.
Yes.
Yeah.
So that kind of page just just read.
So that is what precision recall trade-off is. Now, this is very interesting. Now you have precision and recall. Now you don't have any criteria to choose high precision and high recall. And I also have to answer another question: why we need to have precision and recall when you already have accuracy? By now, I think you would be able to figure out why precision and recall also matter. In not all cases will answer accuracy. Accuracy doesn't actually answer every of your case. In some cases, you want to have precision. Precision is not something equal to accuracy. They are not related. Whereas recall and precision are interrelated, because when we have high precision, we have low recall. When you have low recall, we have high precision. So that is why you need in some business cases, precision and recall also has to be considered when you have. It is not just the prediction that matters to you. What does matters to you? You have some business case where you want to have less positives or you want to have less negatives. That is the reason there are some other metrics which actually uh, tells you which classifier has to use in such cases. You have seen the email case, spam, the cost of moving in genuine email, for example, an important offer letter or a business contract to a spam email. That's very costly. If you don't go or if you don't reply within a specific time, you will lose that complete offer. They will no more accept. I mean, they no more take you to the organization as an employee if you don't accept that email or the offer letter within a stipulated amount of time, right? So that is costly. In that case, you want to reduce false positives. If you take contagious some contagious diseases like corona, it is okay to classify or predict a patient with uh, who is not infected with corona as a corona patient, but it is harmful to classify a corona patient as not corona patient, because he will infect other patients as well. So in such cases, accuracy will not tell you anything. Only precision and recall will tell you which classifier has to use. Now we always tend to you have seen, let's suppose I have three algorithms. Okay, algorithm 1, algorithm 2, and algorithm 3. I have precision and recall. Okay, the precision is 0.5, 0.4, 0.7, 0.1, and the other precision, and the precision for the third algorithm is 0.05, and the recall is 1, right? Now it is interesting. You don't have any specific requirement. Let's suppose if you want to have high recall, you go with this algorithm, and if you want to have high precision, you go with this algorithm too. And you don't if they both has to be somewhere around equal, you go with this. But out of all these three algorithms, and if you don't have such requirement like having high precision or high recall, you don't have such requirement. But how can you go with a single, how do you choose which algorithm is best? Okay, that is your case, right? That is your case. Interesting. Okay, so now you want to find out, you know, um, which you want to go with a single algorithm. You want to find out which algorithm is best for you to go and use that, right? Algorithm means which model you want to go with. So if I go with an average value, okay, let's suppose I want to just go with a single number that tells me. So I have two numbers here. What I'll do, I don't have any specific requirement for precision and recall. So then what I'll do is I'll take the average of both of them. And then let's take the average of both the values, and then you can choose it. So if you take the average of these two values, what will be the value of this 0.5 plus 0. This becomes 0.45 by 2, right? This becomes 0.45. I'm taking average of precision and recall. Average is nothing but precision plus recall by 2, because I'll get one number. Then I can compare all the numbers. I can compare these single digits, and then I can choose one model. If I take 0.7 plus 0.1, it becomes 0.4. So if I take 0.05 plus 1, this becomes 0.5. So if you look at these numbers, I see this is the best classifier, right? 0.5 is the highest number of these three. So I can go with algorithm 3. Okay, so that is what, if you take the average value, that is what you're getting. But is this really a right, is this really a good classifier? Precision is 0.05 and 1. Is this really a good classifier when compared to these two classifiers? Let's understand that. Can you tell me, can you fill this confusion matrix for this case? For this particular case, can you tell me what are the values in this confusion matrix? Thank you. Did we recorded that average stuff? No.
Yes, we have recorded average.
When did we stop then?
While calculating this confusion matrix. The result we haven't recorded, I guess, but the previous.
Oh, sorry. So we're actually trying to find out the average. Average is, if you take the average, if you want to come up with a single value for precision and recall, I'll take the average parameter now. Average is equal to precision and recall. I got this value as 0.45. I got this as 0.4, and I got this as 0.5. So if I take the average, if I want to come up with a single value from precision and recall to represent, I mean to see which is the good algorithm, then these are the average values, and these values says that algorithm 3 is the best performing algorithm. But let's, if you take this example here, we got 5 here as true positive, 95 as false, I mean false positives, and 0 here and 0 here, and the precision for this is coming down to be 0.05, because 5 by 100, 0.05, because 5 by 5 plus 95, which is 5 by 100, precision is 0.05. R is equal to recall is 1 here, 5 by 5 plus 0, which is 1. So this case, whereas you have 95 not spam emails, okay, but this model is classifying everything as spam emails. So this is same as this, okay. And if you take the average of precision and recall to come up with a single value, it is saying this algorithm is best. But in the real world scenario, if you take this example and calculate this precision and recall, they're matching these values. And the model is not at all performing well. It misclassified 95 not spam emails as spam emails. So this says average is not a right right single value representation for precision and recall. Then what is the right representation of precision and recall if you want to come up with a single value? Let's see calculating the harmonic mean of precision and recall. So the harmonic mean of any two numbers is given as 1 by 2 into 1 by p plus 1 by p plus 1 by r. So 1 by f is equal to harmonic mean of two numbers is equal to 1 by 2 into 1 by p plus 1 by r. So if I come up with this particular value, so this comes to be 1 by f. Harmonic mean of p and r is given as 1 by f is equal to p plus r by 2pr. So harmonic mean of precision and recall is given by 2 into pr by p plus r. So if I calculate this f value for this, okay, I'll let you know what is that f and all that stuff. Just I'll come back to that again. So now I know that average is no more a good parameter or good single value representation of precision and recall. Now let's go calculate the f values for these three algorithms with different precision and recall values. If I go calculate the f score or the harmonic mean of precision and recall, instead of f I'll say harmonic mean of f. And now we know that average is not a good parameter to generalize precision and recall. I'm coming up with something called as harmonic mean. Now can you tell me what is the harmonic mean of 0.5 and 0.4? It is 2 into, the others can calculate for algorithm 2 and 3. So I'm just calculating for algorithm 1. So that becomes, so if I want to calculate this harmonic mean, it is just like 2 into 0.5 into 0.4 by 0.5 plus 0.4. Okay.
0.4.
So for the first one, it is 0.4.
Yes.
Okay. So the first one, it is 0.4. What is for the second one?
0.17.
Point
175.
0.175, right? 175. What is for the last one?
Point 6.
0.6.
Yes.
No, it is 0.095, right? This is 2 into 0.05 into 1 by 1 plus 0.05, which is 0.095. Now, if you consider this harmonic mean, it says this is the worst algorithm, right? The value is very, very low. That says this is the worst algorithm, whereas the best algorithm is algorithm 1. Okay. If you look at this, where do you get somewhere around equal precision and recall when you have threshold somewhere in middle, right? So this is the best algorithm. So harmonic mean of precision and recall is coming down to be the best single value representation for precision and recall, right? So this is the best algorithm. So when you want to combine precision and recall, and if you want to come up with a single value, you have to take the harmonic mean of precision and recall. So that harmonic mean of precision and recall is called as F1 square, F1 score. Okay. F1 score is a metric that combines precision and recall into a single value. So combining precision and recall into a single value is called as F1 score, serving as a harmonic mean. It is useful when both precision and recall are equally important. Okay. When precision and recall are equally important, so then you have to find out F1 scores, and based on the F1 scores, you have to actually come up or choose an algorithm or come up with an algorithm. Okay. This is self-explanatory basically. So when y pressure is, let's suppose when pressure and recall are important, when recall is low, the total value of F1 will be low. When pressure is low, pressure low into high will be low, right? So F1 will be low. When either of pressure or recall are low, F1 will be low. When both have equal importance, if you see both have equal importance, in that case F1 will be more. So the multiplication value will be more, F1 will be more. When one is less and the other one is more, then the F1 score will be more. So F1 score has to be considered when both precision and recall are important, right? When false positives and false negatives are also important, then you will go with F1 score. Understood? So that is what basically F1 score means. Now going back to the next one. Now we want to understand when you have accuracy, why F1 score, right? Or precision and recall. Precision or recall are different cases. F1 score is again a single value. Okay. It doesn't have any specific requirement. So it says both precision and recall. I mean, precision and recall are important. That means false positives and false negatives are also important. That is similar to accuracy, right? So F1 score is especially helpful in imbalanced data sets where high accuracy alone cannot be misleading. High accuracy alone can be misleading. So when you have imbalanced data sets, accuracy is misleading is what that sentence says. Now, how it is misleading is what we will study now. Okay. Anyways, when did we study these imbalanced data sets? Do you remember in Kernel, we studied these imbalanced data sets and we have found out some solutions. Do you remember that? Can you tell me what to be done in KNN when you have imbalanced data sets? Hello? K value has to be high or low when you have imbalanced data sets and using KNN. K nearest neighbors. K value has to be low so that only few items will be in the circle and you can find out the highest number of points closest to the test point and all the stuff. There we have studied imbalanced data sets basically. So what happens when we have imbalanced data sets is that if you look at that, what is an imbalanced data set? Imbalanced data set means one class will have more number of points, whereas the other class will have less number of points. Let's suppose if you take this case, if you have 1,000 transactions, out of them 100 are fraudulent and 990 are legitimate or a good transactions. So out of 10,000 transactions, 10 transactions are fraudulent transactions and 990 are legitimate transactions. That is how the real world transactions also would be. Most of them will be legitimate, but only few will be fraudulent transactions. But you cannot miss those fraudulent transactions. Those are important to find out, right? Now, if you calculate the accuracy for this, okay, if you calculate the accuracy for this, what will be the accuracy for this? Accuracy, can you tell me what is the accuracy of this? Accuracy. Accuracy is true positive plus true negative by all of the values, right? So 990 plus 0, that is true positive, false positive, true negative, false negative. Sorry, this is false negative and this is true negative, right? If you take prod as positive. So 990 plus 0 by 0 plus 10 plus 0 plus 990. So that is 990 by 1000, which is 0.99. That means the accuracy of this model with this confusion matrix accuracy is showing as 0.99. But what is happening? It is actually predicting all the fraudulent transactions as legitimate transactions, right? The model is by just looking at the confusion matrix, you can say it is not able to find out any fraudulent, or it's not able to predict or classify any fraudulent transactions. It is classifying everything as legitimate. It missed all the fraudulent transactions, or it classified all the fraudulent transactions as legitimate transactions, but still the accuracy is coming as 0.99. So this accuracy is not at all rightly representing, or you cannot consider this as a parameter or the performance matrix of the imbalanced data sets, because in this you see this is an imbalanced data set, but accuracy of this on this imbalanced data set you have applied a model, and that model is classifying or not able to predict any of the fraudulent transactions. The model completely failed to find out the fraudulent transactions, but still the accuracy is showing as 0.99. That means very high accuracy even if the model is not performing well. So that's the reason accuracy cannot be used in these cases. When you have imbalanced data sets, accuracy alone is misleading. So this accuracy says the model is performing greatly, but that is not true. If you can you calculate the precision, recall, and FN score for this? What is the precision for this? What is the precision for this? What is the recall for this, and what is F1 score for this?
Zero.
Precision is 0. What is recall?
0.
What is F1 score?
Zero.
F1 score is 2 into PR by P plus R, right? So this is 0. So now in this case, these metrics are rightly representing the classifier, right? So everything is 0. That means it says the classifier is not doing good, but accuracy is saying that the classifier is doing very good, right? So F1 score here is 0, revealing that the model performs very poorly in detecting fraudulent transactions despite its high accuracy. In fraud detection, missing actual fraud cases is critical, right? Therefore, focusing on precision, recall, and F1 score is more meaningful than accuracy. So in such cases, precision, recall, and F1 score is making more sense. Accuracy is misleading you. So that is the reason you need multiple performance matrix. It's okay to calculate every performance matrix and you make sure everything is right to make sure the classifier, you are choosing the right classifier. So just calculate accuracy, precision, R, F1 score, and everything, and see how and analyze the different metrics, and then come up with a decision. Don't just rely on accuracy itself alone. So accuracy is misleading you. So calculate every other parameter and just come up with something that you want to have or choose something. Okay, that is why you have multiple performance metrics. So that's why I'm saying accuracy alone cannot help you to choose any of the models. Understood? Okay, so that's a great discussion so far, but from now onwards this is the other part of this performance metrics. Okay, this is also very important and little tricky to actually understand this. So now we are talking about specificity. So we talked about sensitivity. What is sensitivity? Do you remember this? I'm saying recall can also be called as sensitivity, right? Where is that? Recall is also called as sensitivity or true positive rate, right? If you look at this, recall is also called as sensitivity or true positive rate. Okay, and remember that true positive rate. What is recall means? Out of all the actuals, how many positives are rightly classified is called as recall. Recall is also called as sensitivity. And now we are talking about specificity. What is specificity? Specificity is also called as true negative rate. Sensitivity is true positive rate and are also called as recall. Specificity is true negative rate, or we can also call it as selectivity. Specificity is, okay, true negative rate. Specificity. 1 second. False positive rate. Okay, for true negative rate. Okay. All right. Specificity is defined as true negative by true negative plus false positive. Okay. So what is recall? Recall is true positive by true positive plus false negative. This is recall. What is recall says? Recall says out of the actual positives, how many are correctly classified by the classifier. Okay. That is what recall is. What is sense? Sorry. What is specificity? Recall is also called as sensitivity. What is specificity? Specificity is true negative by true negative plus false positive. That means how many negatives are correctly classified by the classifier. Out of all the negatives, how many negatives are correctly classified? That is what specificity means. Sensitivity talks about positives. Specificity talks about negatives. How many negatives are correctly classified? How many positives are correctly classified? That is the only thing. Specificity measures the proportion of actual negatives that are correctly identified by the model as negatives. Specificity means how many actual negatives are correctly predicted as negatives by the classifier. Sensitivity means how many positives, how many actual positives are correctly identified as positives by the model. That is the only difference. Okay. How well the model is avoiding false positives. How well the recall is how well the model is avoiding false negatives. Okay. When false negatives is 0, recall is 1. Specificity means how well the model is avoiding false positives. When false positives is 0, specificity is 1. Okay, that is what specificity means. Specificity is particularly useful when false positives are costly or have a serious consequences. For example, in medical testing, high specificity is desired to minimize the number of healthy people being misdiagnosed. And we also have discussed in which cases you want to have less false positives. Yeah, we have taken the spam cases and all that stuff, right? So if it is a rare disease, I'm just putting forward some other example here. When you're trying to find out a rare disease, okay, yeah, where medical screening for a rare disease, let me just read this so you'll understand. Low disease prevalence. If the disease is rare, the majority of the people tested are healthy. That is what rare disease means, right? Most of them will not be um, tested as positive for that disease because that's a rare disease. A high specificity will ensure that most healthy individuals are correctly identified as negative, reducing the number of people who will receive false positives. If they are healthy and if they are predicted as not healthy, what happens? I mean, infected or not infected. So this is infected, positive. This is not infected by the rare disease. If someone who is not infected but predicted as infected, then what happens? It will give him some mental stress. He has to go with some additional tests of unnecessary worry and stress for the patients, additional tests, extra healthcare costs. All of them will be incurred unnecessarily on that patient if he is wrongly identified. In that cases, false positive is important. We already have discussed so many examples and I don't want to repeat that again. So specificity is just like it's just a measurement to see how the model is performing on the negative values, whereas recall or sensitivity is something which concentrates on the positive values of that, how the model is performing in the positive values. In this context, a high specificity test minimizes the number of healthy people who are incorrectly flagged as having the disease. That means we are minimizing the false positives in specificity. Okay, that is all you already know. They are all interrelated. Specificity versus sensitivity. Specificity focus on correctly identifying negatives, whereas sensitivity focus on correctly identifying positives. We already have discussed that. In many applications, there is a trade-off between sensitivity and specificity, and which one is prioritized depending on the specific goals and risks of false positive versus false negatives in the application. So it's again application dependent. We already have discussed so many examples, and you would be able to understand it. You have to analyze whether false positives are important for you or false negatives are important for you. If there is a trade-off, you have to come up with what is acceptable trade-off between both of them. Whether both of them has to be equal values, then you have to go with harmonic mean again. The same kind of stuff that we have gone with F1 score with precision recall. The same goes with this one as well, specificity and sensitivity as well. False positive rate is nothing but 1 minus specificity. Okay, specificity is true negatives by true negatives plus false positives. What is specificity? Specificity is true negatives by true negatives plus false positives is specificity. And for that is called as true negative rate, right? True positive rate and true negative rate. Recall is also called as true positive rate. Specificity is true negative rate. Okay. And then now FPR, false positive rate, is nothing but 1 minus specificity. That means specificity is denoted by 1 by Tn by Tn plus Fp. That is, if you just do this calculation, it turns down to be Tn plus, Fp plus Tn plus Fp minus Tn. Tn and Tn will get cancelled. So this turns to be Fp by Tn plus Fp. So false positives by true negatives by false positives. What does false positive rate measures? Proportion of actual negatives that are incorrectly classified as positives by the model. It helps evaluate how often a model incorrectly predicts the positive class for instances that are actually belonging to the negative class. So this says that how many actual positives, how many actual negatives are misclassified as positives. That is called as false positive rate. So we talked about true positive rate, true negative rate, false positive rate. False positive rate means how many false positives are, how many negatives are classified as positives, how many total negatives are correctly classified, how many actual negatives are correctly classified as negatives by the model, how many actual positives are correctly classified as positives by the model. FPR says how many how many negatives are classified as positives. Okay, that is called as false positive rate. It is particularly important cases where false positives are costly or problematic. Okay, these are all interrelated. You can use anything what you want to use. But why we studied false positive rate is there is something called as ROC curve, which helps to analyze which model is best. Okay. So ROC curve is a plot between true positive rate and false positive rate. False positive rate is nothing but 1 minus specificity. Recall is nothing but sensitivity. True positive rate is also called as recall. When you draw a graph between these two values, we call that as ROC curve. Okay. What is this ROC curve? ROC curve is something which summarizes all the confusion matrix that each threshold produced. Okay. Let's go one after the other and you will understand this clearly. This ROC curve is very important. AUC curve, ROC curve, and all that stuff. I think we are close to completing all the stuff in a short. Right. So let's understand this ROC curve. The plot between true positive rate and the false positive rate. And you also know the formulas by now. That is fine. So what is this ROC curve is that it generalizes or summarizes all the, it summarizes all the confusion matrix that each threshold produced. Okay. It summarizes different confusion matrix into a single graph. Okay. If you look at this, we have come up with multiple, we have come up with multiple, where is that? In this particular slide, by changing the thresholds, we come up with different, what are this? Different confusion matrix. So you cannot keep, if you have more number of thresholds, like if I come up with, here we have 4 thresholds. So like if you have 100 thresholds, then what happens? You will have 100 confusion matrix, right? You cannot keep track of all of them. Okay, in this case, if you just go to this particular graph, the threshold is 10,000, 75,000, 50,000. You have around like 7 divisions here or 7 units specified here. Then how many confusion matrix you'll have? You'll have around 9 confusion matrix for this particular values of thresholds. So combining all these confusion matrices into a single graph is the ROC curve. That is what ROC curve will do. It consolidates or summarizes multiple confusion matrices into a single graph. Okay. Now, what I'll do is, for a threshold of 0.95, I'll come up with an ROC curve. Okay, I'll come up with the confusion matrix for that particular threshold. Let's suppose this is my data. Okay, this is the same data that we ever discussed. So let's suppose 1 is called as spam and 0 is called as not spam, and these are the probabilities. We already solved this example before, the same example. Okay, but there is 1 and 0 are represented, spam and not spam are represented by 1 and 0. That's the only thing. Okay, let's suppose for this threshold we came up with a confusion matrix. Okay, so in this confusion matrix we come up with some values: true positive, this is false negative, this is false positive, and true negative. And now we know what is recall. Recall is nothing but TP by TP plus Fn, that is recall. And what is false positive rate? Recall is true positive rate, right? Recall is true positive rate, and false positive rate is nothing but Fp by Fp plus Tn, right? Fp by Fp plus Tn. That is what? False positive rate, right? Is that right? False positive rate Fp by Fp plus Tn. If you look at this, we are covering everything. In recall, what we are covering? We are covering these two things. In FPR, we are covering these two things, right? We're covering all the values of the confusion matrix with these two parameters. And now this confusion matrix is plotted as single point on the graph. Okay. Now for this threshold, for this particular threshold, you will get another confusion matrix, right? That's what we have calculated before. And now this confusion matrix is converted into a point by using recall and false positive rate, and you're trying to do that. So why only false positive rate? Can't you go with true negative rate? Yes, you can go. You can even go with precision, or you can go with recall. It depends on the criteria that you choose, what is giving you the right graph. It doesn't necessarily needs to be true positive rate and false negative rate, but ROC curve is something, that curve is the graph that is drawn between true positive rate and false positive rate. Okay, true positive rate and false positive rate. So it's, instead of going for true negative rate, it is going with true positive rate. So now do you understand why we call ROC graph as summarization of confusion matrices? Because for every threshold we get one confusion matrix, and that confusion matrix is converted into a point form by calculating recall and false positive rate, and that point is represented on the graph. Now we have 4 thresholds here, so we have 4 different points. Okay, 0.2 and 0. For threshold 0.95, true positive rate is 0.2 and false positive rate is 0. Okay, so this is the threshold for 0.95. Okay, 0.6 and 0.2. For threshold 0.80, it is 0.6 and 0.2. Oh, 0.6 and 0.2. Sorry, 0.2 into 0.6. So 0.2, 0.6. This is threshold 1, this is threshold 2, and this is 0.8, 0.6, 0.8. This is 3. So this is x-axis and this is y-axis. 0.6, 0.8 is represented by this, 0.8 and 0.1 is represented by this. Got it? So now every threshold we'll have one confusion matrix. Confusion matrix is represented as a point. So if you have n number of thresholds, they will be just represented as points. So this is called as ROC curve. Okay, ROC curve is just a graph between true positive rate and false positive rate. That's okay. Now, how does this ROC curve help us? Okay, that is what you have to understand. So there are few things that you have to understand here. Okay. So now when you draw an ROC curve, from the ROC curve, you can interpret that whether your model is performing great or not. So how do you compare? You want to compare that with this random classifier. This line you see, this line says in this particular line, TPR, false positive rate, is equal to true positive rate. Okay, that means false positive rate is equal to true positive rate for this random classifier. What is a random classifier? Random classifier is nothing but a random classifier assigns labels to instance purely by chance without using any knowledge or patterns in the data. That means randomly choosing a class for it. Let's suppose you have 10 emails. Okay, I mean, let's take another example. Let's suppose you're not using any predicting model. You have 100 emails in your basket. If you have 100 emails in your basket, randomly, if you're getting one email, you're blindly saying that as spam. You're saying that as spam. And if you're taking a third email, you're just normally saying that as, you're not using any knowledge, any patterns in the data. You're randomly saying that this is not spam, not spam. So in that case, what just happens? There would be an equal probability between spam and not spams. Okay. So that's called as random classifier, and this line represents a random classifier where FPR is equal to TPR. Okay, whereas false positive rate, and for the random classifier, false positive rate is equal to true positive rate. That means true positive by true positive plus false positive is equal to, sorry, false negative is equal to false positive by false positive plus true negative. Okay, so that turns out to be these two values are equal. You're getting that? So false positive rate, this is false positive rate and this is true positive rate, so they both are equal. So let's do that math and see what happens. TP FP plus TP TN is equal to FP TP plus FP TN. Okay, so what we are doing, we're just multiplying this with this with this. So TP FP gets cancelled. So TP TN is equal to FP TN. That means,
It's FN.
sorry, where is that?
FPTN, it's FPFN. The last time.
Oh, sorry, this is FPFN. So this is FPFN. Pointer options. So this is FPFN. So FPFN. So that means what this, from the confusion matrix, what does this look like? So this and this would be equal number. The probability of this is equal to this, basically. That means the probability of unpredicting something, wrongly predicting something is same as probability of predicting something as true. That means TP by FP. I would say this, FP by TP is equal to FN TN by FN. P by TP is equal to TN by FN. Okay, basically this itself will says the probability of this would be equal to this. That is what basically random classifier means. There is an equal probability for choosing for assigning the random classes, different classes or equal probability for all the classes. That is what basically random classifier means. Now, how to interpret this ROC curve is something that we have to study. So benchmarks the diagonal line serves as a baseline for evaluating model performance. So this acts as a baseline. So this random classifier where TPR is equal to FPR acts as a baseline. Okay, that means above the diagonal, a model that performs better than random. So if the line, if the model that performs above the diagonal, if the ROC is above this diagonal, that says the model is performing better than the random. If it is much farther above that particular line, the model is performing great. Below the line, the model that performs worse than random, which might indicate issues like improper training or flipped labels. If this is below, if the ROC curve is below below this particular line, then there is a problem with this model that is performing worse than random prediction. Like even if you don't train the, if you don't use any knowledge, or if you don't use any patterns in the data, just randomly assigning some class to the data points, if the model is performing worse than that, then there is a problem with in training the data. So this serves as a baseline. The random classifier line, or this straight line where TPR and FPR is equal, serves as a baseline. And if the ROC curve is above this particular line, then we say the classifier is doing good, or the model is performing better than the random. That is what ROC curve is. Okay. What is AUC curve? AUC is nothing but area under the curve. Area under the ROC curve is called as AUC curve. Okay. How to interpret AUC curve? AUC curve makes it easy to compare one ROC to another ROC. Okay. One ROC to another. Let's suppose if you have two models. This is model 1's ROC and this is model 2 ROC. Okay. Now you have to tell which is a good algorithm or model. The area under the curve for red ROC curve is greater than the AUC, area under the curve for the blue ROC. That means area under this curve is greater than the area under this curve, right? That is true. That is clearly visible. Even though the ROCs of both the algorithms, okay, or both the models. This is, let's say this is model 1 and this is model 2. Both the models are performing better than the random classifier, because the ROC curves of both the models are above the random classifier. They both are doing good, but which is good out of these two? AUC area under the curve can tell that, as the area under the curve of red curve is greater than area under the curve for model 1, which is red, is greater than area under the curve of model 2, which is blue. So as area under the curve for model 1 is highest, you can say model 1 is the go-to model for your classification. That is what AUC curve tells us. Area under the curve. AUC for the red ROC curve is greater than the AUC for the blue ROC curve, suggesting that red curve is better. So if the ROC curve represents model 1 and ROC curve and blue ROC curve represent model 2, you would use model 1 for the classification. So that is all about ROC and AUC curves. Okay. Receiver operating characteristic curve, which is ROC curve, which is a graph between true positive rates and false positive rates. False positive rates is nothing but 1 minus true negative rates. True negative rates is also called as what? Specificity. Specificity is represented by true negatives by true negative plus false positives. Okay. Where is that specificity? Yeah, here it is, true negative by true negative plus false positives. So that is all about AUC curve and ROC curve and AUC curve, receiver operating characteristics curve and area under the curve. Now, you calculated the sensitivity and specificity for a 2x2 binary classifications, right? So for binary classifications, it would be a 2x2 matrix. Now, how to calculate the sensitivity and specificity for 3x3 or multi-class classifiers? You don't really need to do this on the paper, just for your understanding. Like I would like to put this forward, like how to calculate the sensitivity and specificity from multi-class classifiers. Okay. How do we do that for multi-class classifiers? Okay, let's see if you are able to calculate the sensitivity for this particular 3 by 3 matrix. So this is the confusion matrix given for 3 by 3 curve. This is the confusion matrix given for, sorry, what's going wrong? What is the confusion? I'll give some pause after this slide, and then we are going to talk about something which is very important, which is ensemble learning. Okay, so I'll give a break for 15 minutes and then we will start this ensemble learning back again. Okay, but before starting this, let's go understand this. Right. So can you, if you truly understand the meaning of sensitivity and specificity, it would be easy to calculate, but let's see if you're able to do those calculations or not. So go back here. This is the confusion matrix given for 3 by 3, right? 3 by 3 matrix. Now calculate the sensitivity and specificity. What is sensitivity? Sensitivity is nothing but recall, right? Let me write the formulas for you. So sensitivity is nothing but recall. Recall, what is the formula for recall? What is the formula for recall? Hello.
Yeah. Hello.
What is a recall?
Formula. Fp by Fn plus Fp.
What is that?
Fp by Fn plus Fp.
Sensitivity.
Yeah.
Sensitivity is also called as recall. What does recall measures? What is recall? What does recall measures? Recall measures how many actual positives are predicted as positives by the model. That is right, true positive rate. Right, true positive rate. That is true positive by true positive plus false negative. That is what recall means, right? Then what is specificity? Specificity is nothing but true negative rate, right? That is Tn by Tn plus Fp. How many actual negatives are predicted as negatives by the model? That is what specificity actually means is. Now, can you calculate the sensitivity for troll 2? So it is asking us to calculate sensitivity for troll 2. That means it is asking us to calculate the sensitivity for troll 2. Now, can you tell me what is the sensitivity of troll 2? Now, do you understand? Do you understand this 3 by 3 matrix? If you carefully observe this, so these are actuals, these are predicted, right? So these are predicted. So now it it predicted 12 correctly. So it predicted troll 2 as troll 2, but it predicted 102 Gore police as troll 2. It predicted 93 cool as ice as troll 2, right? Sensitivity tries to find out of all the actuals, how many are rightly, how many positives are rightly predicted, right? So what are the total actuals of troll 2? These are the total actuals of troll 2, right? Out of all the actuals, how many are rightly predicted? Understood? So these are total number of actuals of troll 2. So if you are given a data set, these are the total actuals of troll 2. Out of all these actuals, how many are rightly predicted by the model? Only 12 out of 12 plus 112 plus 83 are rightly predicted. So sensitivity becomes 12 by 12 plus 112 plus 83. Understood? So these are actuals. So how many total troll 2s? How many total actual troll 2s? 12 plus 112 plus 83. Those are the total actual troll 2s. Out of these total, how many are rightly predicted? 12 are rightly predicted. So that is 12 by 12 plus 112 plus 83. That is called as recall. Understood? Understood or not?
Yes.
Now you want to calculate the specificity for troll 2. What does specificity is? Specificity says, now let me keep um, sensitivity aside. Now we are trying to calculate the specificity for the same thing. What does specificity tries to find out? Specificity tries to find out how many negatives are correctly identified. That means um, how many points which are not troll to are rightly identified. So if you look at this, these are predicted as troll 2s. These are actual troll 2s. Okay, which are not troll 2s. These are not troll 2s. Right, these four are not troll 2, and the model also predicted them as not troll 2s. Right, the model predicted them as Gore Polis. The model predicted these values as the model predicted all these three as cool as S, all these three as Core Polis, all these three as troll 2. But these are troll 2s. 112 and 83 are troll 2s. These are actual troll 2s, but it predicted wrongly. What is true negative rate tries to measure? True negative rate tries to measure how many did it find out, how many actual negatives are are correctly identified as negatives. So only these four rows are identified as negatives, right? So these four rows are identified as true negatives. So true negatives would be 23 plus 77 plus 92 plus 17. These are true negatives. And now, what are false positives? False positives means they are not actually troll 2s, but model predicted them as troll 2s. They are not actually troll 2s, but model predicted them as troll 2s. So these two are something, the model predicted them as troll 2s, but they're not actually troll 2s. Okay. Understood or not? Any questions? Hello?
Understood.
Now it's time for it. Now tell me, let me erase everything and let me ask the questions directly now. I'm erasing everything. Now tell me, what is the sensitivity for Gorepolis? What is the sensitivity for Gorepolis?
Twenty-three by 102 plus 23 plus 92.
You're telling about sensitivity, right? What is the sensitivity?
Sensitivity. 23 by 102 plus 23 plus 92.
102 plus 23 plus 92. Fantastic. This is sensitivity. So out of all Gorepolis, out of all actual Gorepolis, how many are correctly predicted is called a sensitivity. So um, don't ever remember the formulas. Okay, always try to remember the concept so that it would be easy for you to you know calculate the values. Now tell me, what is specificity for Gorepolis? Specificity for Gorepolis.
True negatives would be 12 plus 93 plus 83 plus 17.
True negatives would be 12 plus
93 plus
8,
83 plus 17.
20. Okay.
And false positive would be 0 false positive. So 102 plus 92.
False positives would be 102 plus 92.
92.
False positives is 102 by 92. Is that right?
Oh, no. 112 plus 77.
Yeah. Awesome. That's good. So if you look at this, what are true negatives? Specificity is true negative by true negative plus false positives, right? So true negatives means which are not Gore police are correctly predicted. So if you look at this particular diagram, what are so let's come back to this diagram. So true negatives, that means which are not Gore police are truly identified as not Gore police. If you look at this, this is not Gore police. So model predicted them as troll 2, right? So this is not Gore police, correctly identified. This is not Gore police. This is not Gore police. This is Gore police. This is actual Gore police. It also predicted that as. So what is specificity? Specificity says true negatives by true negatives plus, what is specificity? True negatives by true negatives plus
True
false
negative,
positives.
false.
So true negatives means, what are true negatives? Which are not Gore police, which are out of actual negatives, how many are truly identified as negatives? Okay. So in this case, is this true negative? Is this part of true negative? 92.
No,
Why?
because it identified as cool as ice, but it is actually Gore police.
Right. They're actually Gore police, but it identified them as cool as ice. But what are true negatives? True negatives means Gore police has to be, true negatives means which are not Gore police has to be identified as not a Gore police. But it is Gore police, but identified as cool as ice. So what does this become? So this is, this becomes like, we see that representations, right? What is false? What are those representations? I do false positives only. Yes, everything is false positive to false positives. Okay, so everything is represented as false positive. So this is false positive of, this is Gore police identified as cool as ice. Okay, so that's why you got only these four as true negatives. Now what are false positives? False positives means they are predicted as Gore police, but they are not Gore police, right? So what are not Gore police? These two are not predicted as Gore police, but they are not Gore police. So this becomes 112 plus 77. That is specificity. Okay. Now that's good. We completed this. We completed this, and this is clear over here. Specificity we completed for troll 2. We completed for this. Now cool as ice is pending. Now it's easy. The practice is something that is all that needed. Now tell me what is cool as ice. I think it would be faster. What is sensitivity?
17 by 93 plus
17
by
Mhm.
93 plus 77 plus 17.
93 plus 77 plus 17. Is that
Seven.
right?
Yeah.
What is sensitivity? Sensitivity is given as true positives by true positives.
Positive by true positive plus false negative.
How many of total Coolidge ice are identified as Coolidge ice? So 17 by 17 plus. So out of all actuals, only 17 are identified rightly. So that becomes 17 by 93 plus 77 plus 17. Now what is specificity?
Specificity. 93 plus 77 plus 17 plus 83 plus 92.
What are they? Tell me again.
93 plus
93 plus. So specificity is what is specificity?
77 plus
Two negatives
true
by
negative by true negative plus
false.
false positive.
What are true negatives? True negatives means
90
not Coolidge ice are identified as not Coolidge ice.
is all
Coolidge ice.
93 plus
Okay, so this 93 is cool as ice, but that is predicted as troll 2, right?
true.
What is true
Yes.
negative? True negative means which are not cool as ice should be predicted as not cool as ice, right?
Okay.
12 plus 1 or 2 plus 1, 12 plus 20.
12 plus 1 or 2 plus 1, 1, 2 plus
112, 112 plus 20.
Plus 23.
what is false positive now?
83, 92.
83, 92. These are false positives. They are predicted as cool as ice, but they're not cool as ice. So that is what the calculation of sensitivity and specificity for 3 by 3 or multi-class confusion matrix. Okay, you can calculate anything, accuracy or whatever it is. That's fine. Can you just calculate the accuracy for this? Let's see. Can you calculate the accuracy for this? What is accuracy?
True positive plus true negative
Mhm.
by sorry. Yeah, it's all
It's all. Okay. Now, what are true positives here?
12, 23, 17.
Awesome. So true positives means they have to identify it as same thing. What are true negatives here? Okay, I'll give this as for you to actually. I mean, all try to also calculate precision, recall, and all that stuff. So all you have to calculate is TPTN, FPFN. That's all. Once you are able to calculate that, you will be able to calculate any of the matrix. Okay. Now I'll just pause this for 15 minutes. If you want to try, give it a try for this. So this is an interesting thing that we're going to study now. Ensemble learning. So the main idea behind this ensemble learning is that instead of choosing a strong predictive model or strong algorithm, combining multiple weak learners or weak models together and accumulating or aggregating the results given by the weak learners and making a prediction is much stronger. So basically in ensemble learning, what we do is we take multiple weak learners and combine or aggregate the results given by them and make the prediction instead of just going with a single strong predictive model. That's what ensemble learning basically means. Is in ensemble learning, we combine multiple weak learners. What are weak learners or weak models? What are a weak learner is basically a machine learning model that performs slightly better than random guessing. So what is random guessing? We already have seen that in the earlier case, right, where the true positive rate is equal to false positive rate, right? So this is the random classification. So a weak learner is something which will slightly perform better than this random guessing or the random classifier. Those are weak learners. So weak learner is a machine learning model that performs slightly better than random guessing. In the context of classifying tasks, a weak learner has an accuracy just above 50%. Accuracy just above 50%. 50% is, let's suppose 50% is the accuracy of random guessing. The accuracy of these models is just above 50%. Similarly, for regression tasks, a weak learner produces predictions with performance marginally better than the. So the baseline is basically just the mean value. So if you have multiple means, the mean value is the baseline parameter for regression tasks. So these will perform slightly better than this uh, that baseline values. So weak learners are just like a basic machine learning algorithms. So what we do is in ensemble learning, it's a technique. Ensemble learning and machine learning is a technique where multiple models, often referred to as weak learners, and we just learned what a weak learner is, are combined to solve a particular problem. So we combine multiple weak learners to solve a particular problem. That is what ensemble learning is. The goal is to achieve better prediction performance than could be obtained by a single model alone. So the main goal here is to find out, combined better predictive performance than a single model alone. So when you're taking only single model, there is a high chance of overfitting if it has to perform a much better way. So whereas that overfitting can be reduced when you choose multiple weak learners and taking the accumulated or aggregated result of that. How do we combine multiple weak learners? What are the different ways of combining different weak learners is something that we're going to learn now. The underlying principle is that group of weak models working together can outperform a strong individual model. Okay, so group of weak individuals can outperform a strong individual model. It is just something like if a strong person is fighting with 100 weak persons, there is high probability that the weak persons will win the game, right? Similar to that. Ensemble methods are widely used because they reduce the risk of overfitting and improve generalization. So if it is a strong individual model and if you train that, there is a high chance that it may get overfitted. If it and it would have high variance. That means you know what is variance and what is bias. Variance means the predictive performance will vary highly when compared from test data to the training data. Okay, so the model will perform slightly different on the testing data sets. That's called as high variance. So different types of ensemble methods are bagging, boosting, stacking, and noting. We will come back to everything shortly. What does they actually mean? These are like different ways of combining the weak learners. Okay, each bagging will have a different way of combining the weak learners. Boosting will have a different way of combining the weak learners. Stacking and voting the similar way. Okay. let's, as I told you, different weak learners are combined to do the prediction. So different weak learners will become a strong learner. So when different weak learners are combined, they will become a strong learner. That is what ensemble learning will technique will actually try to do. Okay, now let's understand, let's see how do we combine multiple um, weak learners. What are the different ways of combining the weak learners and all that stuff. Okay, so that is what basically ensemble learning is. Ensemble learning main goal is to combine the different weak learners so that they together will outperform a single best model. Okay, going back to the next slide. So before going back to different ensemble learning techniques, you have to understand what is bootstrapping is. Bootstrapping is a technique, statistical sample technique that involves drawing random samples with replacement. Okay, bootstrapping is drawing random samples with replacement from a data set to estimate the population statistics or create new data sets. We do bootstrapping to estimate the population parameters or population statistics. So why do we do sampling? We cannot estimate the parameters of the population. So to estimate the parameters of this population, we take the sample from that population and then we try to estimate the parameters of the population or statistical parameters of the population from that particular sample. So bootstrapping is a technique where we randomly we sample or we draw random samples with replacement. Drawing random samples with replacement means, let's suppose this is the original data set. Okay, let's suppose this is the data set that is given to you. Bootstrapped data set means we do sampling. Let's suppose I have taken this sample and I replaced it back again. So I taken this sample, replaced it back again. I have taken this sample, replaced this back again. I have taken this sample, replaced this back again. Now again, when I'm sampling, I got the same sample. So when we do sampling with replacement, there are chances that we will get the same sample multiple amount of times. And there is also chances that you will get the same sample 8 number of times. That possibility is also there because you're replacing the sample back again and you're again doing the same sample. So the probability of getting every sample is equal because we are replacing that sample. So that is what bootstrapping basically means. Okay, when you say bootstrapped dataset, you're deriving a sample from the dataset with replacement. That is called as bootstrapped dataset. That is the reason you see you got the same sample twice here. So the total number of samples picked should be equal to the size of the bootstrapped dataset should be equal to the size of the original dataset. Here you have 8 points and here also you do have the same 8 points. So you make sure when you're sampling the size of the datasets to be same, but the replacement can happen. So that sampling, when you sample with replacement, you can get the same sample multiple times. Okay, so this is another example of bootstrapped sample. Okay, so if you look at this, if you look at the third sample, this is also a bootstrapped sample. So what you have done when you are deplacement, you got these two samples twice, this sample twice. The total number of samples is again equal to 8. Okay, so the total number of samples is equal to 8. So that is what bootstrapping dataset means. Bootstrapping dataset means in the bootstrapping, the first step is to make bootstrapped dataset. Okay, in bootstrapping, the first step is making the bootstrapped dataset. Making the bootstrapped dataset is nothing but pick different pick a random sample from the dataset with replacement, but the size of the dataset should be equal to the size of the bootstrap dataset should be equal to the size of the dataset. So that is called as bootstrap dataset. Similarly, usually we do this bootstrapping n number of times and then calculate the statistical parameter. When calculating the statistical parameters, nothing but calculating the mean, median, standard deviation, or any statistical parameter. That would be the second step of the bootstrapping. So first step is making the bootstrap dataset, and the second step is to calculate the statistical parameter of that bootstrap dataset. Let's suppose I have taken two samples here. So I have taken the mean. I constructed a bootstrap dataset and then calculated the mean of that dataset, and I have plotted that mean here in this histogram. And I have taken another bootstrap dataset. I plotted the mean, and similarly I repeated this same process for 1,000 times. So I got different means for different sampling. Okay, and now look at this. After creating thousands of bootstrap samples and calculating the means and adding them to the histogram, we end up for this. Now, what is this 95% confidence interval? 95% confidence interval is that is nothing but when you do a sampling back again, or when you are trying to do a sampling again, and if you try to calculate the mean of that sample again, there is a high probability that that mean of that new sample will fall within this 95% of the 95% of this interval. Okay, so this interval is nothing but where 95% of the bootstrap means will lie. Okay, what does that 95% of bootstrap samples will lie means? Let me take a simple example of you know of a data set, so you will understand what is 95% interval basically means is. So 95% of basically of interval is nothing but if you take this example, uh, you can take the same example here. So uh, if you consider this data set as means, okay, the mean of this is this, the mean of this is this, and all that stuff. Okay, let me pick this. So I have taken this plot which is x-axis, and I'm trying to draw the mean of it. Let's suppose I have 10 samples, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so the mean of this is 2, the mean of this is 2.5, the mean of this is 2.6, the mean of this is 1.8, the mean of this is 1.7, the mean of this is 4, the mean of this is 3, the mean of this is -4, the mean of this is let's suppose this is -3, the mean of this is -10. Okay, now if you plot all these values, so 2 here, 2.5 here, 2.6 here, 1.8 here, 1.7 here, and 4 somewhere here, 3 here, and -4 somewhere here, -3 here, -10 is somewhere here, right? So now out of 10, let's suppose 50% of confidence interval means 50% of confidence interval means what is the interval in which 50% of the means are residing. If you look at this, 5 samples are interval is this one. So this is the interval of 5 samples. Okay, so when you're getting a new, when you're taking a new sample, if you're taking a 11th sample, you can say with 50% confidence that the value lies between 1.7 and 2.6. Okay, that interval 50% confident interval is 1.7 to 2.6. When you're getting a new sample, you can say with 50% confidence that the value will be in between 1.7 and 2.6. Okay, 95% of confidence interval means you take 95% of the samples. So that means 95% of the samples will lies in between this and this. Okay, that means when you're getting a new sample, you can say with 95 confidence that the mean will be in between -4 and 4. So when I say 95% is confident interval means this interval will cover 95% of the means calculated by bootstrapping the data sets. Okay, that is what 95% of confidence interval means. So in bootstrapping process, the first step is to construct a bootstrap data set. The second point is to calculate the mean or the statistical parameter of the bootstrap data set. Keep tracking of the calculations in step 2. We repeat this process 1 and 2. Okay, keep tracking of the calculation involved, and the last step would be repeating the steps 1 and 3 for bunch of times, usually thousands of times, so that we plot all of them, we track all of them, and then you will come up with 95% as of the confidence interval. So with 95% of confidence that when you're doing a new experiment or when you take a new sample, the mean of them will lies between this process. So in ensembling, the major thing that we are concerned about is constructing the bootstrapping data set. That is what we do in some techniques of ensemble learning. Okay, that is what bootstrapping in machine learning basically means is. And now going back to the first type of ensemble learning, which is bagging. When we talked about type of ensemble learning, now we are talking about bagging. Okay, now the first focus of us is to talk about bagging. What is bagging? Bagging means the idea is to train. The idea behind bagging is to train multiple models independently on different subsets of the training data. Okay, train different models or weak learners. Train different models using different subsets of the data, different subsets of the training data. Okay, train different models using different subsets of the training data. That is the idea behind bagging. The idea is to train multiple models independently on different subsets of the training data created by random sampling with replacement. Random sampling with replacement is nothing but bootstrap sampling. Okay, that is called as bootstrap dataset. Bootstrap dataset is nothing but, what is bootstrap dataset? Bootstrap dataset is nothing but random sampling with replacement is the bootstrap dataset. So you take the training data and bootstrap this training data. Okay, bootstrap means if you have 100 rows of this training data, bootstrapping means pick one row, replace that row, pick another row. So this another row can be the same row or any other row from this row. Let's suppose if you're constructing the bootstrapping data out of the 100 rows, how does that actually look like? So you again have to come up with 100 rows, but few rows can repeat again. Okay, this 100 rows has to be picked from this training data set, but this 100 rows can have duplicate rows as well, because we are constructing a bootstrap data set. We already discussed what bootstrap data set is. In bagging, we train different models using the bootstrap data set, and then once we get those results, and then how do we predict? We pick the outcomes of all those models and we aggregate the results, and whichever has the um, highest voting, we classify that particular data as the data point as belonging to that particular class. Okay, that is what bagging basically means. Bagging, this is how bagging actually works. This is how bagging actually works is, so the first step in bagging is construct bootstrap data sets, and those bootstrap data sets will be fed to different weak learners or different classifiers, and these models or classifiers will give an output, and based by aggregating the results given by these different models, we predict the class. Let's suppose if it is a classification problem, we go with majority voting. If it is a classification problem, we go with majority voting. And if it is a regression problem, we go with averaging. Okay, I'll explain you what is major voting and what is regression shortly, and how do we average the results. So let's suppose if you're trying to calculate the height of students in a class, okay, height of students in a class. So we train different models. Okay, height of students in a class is continuous variable, right? It's a continuous variable. So it's a regression problem. So let's suppose if the model 1 predicted the height of the student as 5 feet, if the model 1 predicted that as 5.2 feet, and the model 2 predicted that as 5.5 feet. So the predicted result will become, if this is a regression case, the predicted result will become 5 plus 5.2 plus 5.5 by 3. So that is the average of regression. So this would be the height of the student. If it is a classification problem, if you are trying to figure out if the mail is spam or not. So the model 1 is saying that as spam. Okay. The model 3 is also saying that as spam. And the model 2 is saying that as not spam. Okay. In the classification problems, we go with majority voting. So here the voting for spam is 2 and the voting for not spam is 1. So the majority voting is with spam. So we classify that as spam. Okay. That is how bagging actually works. Bagging is an parallel process. Okay. We have multiple models. Multiple models are trained with, you know, multiple models are trained with a bootstrapped data set, and then the trained model are used to predict the test data set. Okay, so now this is the main idea behind bagging. Let's see how let's see an example for that. Okay, random forest classifier is a um, bagging is an example for bagging technique. Okay, as I told you, bagging is nothing but training the same model, training the model, different models with bootstrapped data set. Okay. So random forest classifier is an example for bootstrapped, I mean bagging example. Okay. So what is random forest classifier and how does this actually works? Random forest is an ensemble learning method. You know what is ensemble learning method? Ensemble learning method is nothing but combining different weak learners and aggregating the results product. Is an ensemble learning product that combines. Ensemble learning is all about combining multiple decision trees. You already know how to construct a decision tree. So random forests will combine multiple decision trees to improve classification. That is what we studied in ensemble learning. In ensemble learning, different weak learners are combined to improve the efficiency or accuracy of the classification. Okay, or regression to improve classification accuracy. It uses bootstrap sampling. You already know what is bootstrap sampling. Row sampling with replacement is called as bootstrapped sampling. So it not only uses bootstrapped sampling, it also uses feature sampling. What are features? Columns are called as features in your data set. Okay. It not only uses bootstrap sampling, it also uses feature sampling with column replacement. Okay. Column sampling without replacement, row sampling with replacement, column sampling without replacement to build each decision tree. Okay, to build each decision tree. That is what random forest is. Random forest combines multiple decision trees, okay, to improve the classification accuracy. It uses bootstrapped sampling data, row sampling with replacement, and future sampling, column sampling without replacement to build each decision tree. Okay, that is what random forest is. You will come to know shortly what that row sampling with replacement and future sampling without replacement and all that stuff. So why we are going with random forests when you have decision trees? Why you are combining multiple decision trees? Decision trees work better with the data used to create them. So decision trees usually works perfectly with training data, but when it comes to the testing data set or the new data set, they will not predict that well. The accuracy of the decision trees on the new samples would be is low. So decision trees work better on the training data set or the data used to create them, but they are not flexible when it comes to classifying new samples. They will not perform that much better or that much well when comes to classification new samples. So that is a drawback with classifiers. So this is a strong learner, but it overfits the data. It overfits the training data, so it will not perform or generalize the data so that it cannot perform well on the test data set. So that's the reason we are going to ensemble learning. What is ensemble learning technique? We are combining different decision trees, okay, by bootstrap sampling. That means sampling the rows with replacement and future sampling columns without replacement to build decision trees. And we construct different decision trees and we take the aggregated result out of all the decision trees, out of the output given by all the decision trees. So this is an example of bagging. In bagging, what we have discussed, in bagging, we have discussed that different models will be trained with different bootstrap datasets, and the aggregated result will be and we use the aggregated result to predict or to classify a particular data point or a new sample, right? Similarly, the good news is that random forests combine the simplicity of decision trees with flexibility, resulting in vast improvement accuracy. So when we combine multiple decision trees, we are improving the accuracy of decision trees. So for a single decision tree, the accuracy is very less because it works perfectly on the training data set, but it will not perform or generalize the data for the test data set or for the new samples. Whereas random forests will combine different decision trees and improves the accuracy, which is an ensembling method, which is called as bagging. Okay, now let's understand how does row sampling works now, and then we can come back to the column sampling or the future sampling again. You already know this. Let's suppose I have 4 rows. Okay, when I create a bootstrap data set, I can actually, when I take the first sample, I got this row. When I do the sampling again, I got this row. When I do the sampling for the third time, I got this row. And I'm doing the sampling for the fourth time with replacement, I got this particular fourth row, right? So first sampling I got second row, second sampling I got the first row, third sampling I got the fourth row, fourth sampling also I got the fourth row. These two are duplicates because we are doing sampling with replacement, so there are high chances that we are getting the duplicates. But this particular row was never picked in this bootstrap data set. Okay, this row is not picked. Typically 1/3 of the original data is not will not be in the bootstrap data set. Let's suppose 1/3 of the data set means it's 4/3. Let's suppose you have 100 rows, okay, in your data. So 1/3 means 100/3. Around 33 rows will not be picked in the bootstrap data set. So what is that remaining data sets is called as? That data set is called as out of bag data set. So this 33 are called as out of bag dataset, which are not picked in the bootstrap dataset. This data is used to train the model. Okay. This data is used to test the model, sorry, not the train. So out of 100, when you're doing the constructing a bootstrap dataset is nothing but random sampling with replacement. So out of 100, usually 1/3 of the data points will not be picked in the bootstrapping dataset. That means out of 100 rows, 33 rows will not be picked in the bootstrap dataset. So these 33 rows will be used to test the model trained using this bootstrap dataset. Okay. Now, so the remaining data set is called as out of bag dataset. Okay. Now, the second step, the first step, as I told you, is constructing the bootstrapped dataset. And the second step is to create a decision tree using bootstrapped dataset, but only using random subset of variables or columns at each step. So once you created this bootstrapped dataset, this is the bootstrap dataset. That's the reason you are getting duplicates. Now, the second step is to randomly sampling, sampling the futures. So when you're constructing a data set for every node, okay, to construct an every node, usually in a decision tree, you will actually calculate the entropy, right? Information gain. Do you remember information gain entropy minus p sigma, I mean log p sigma I is equal to 1 to n. For every point you are calculating the entropy, and then information gain is nothing but difference in entropy of the first row minus previous node. So whichever node has highest information gain, you choose that as the root node. So that is what you have learned in decision trees, right? Now, same concept applies here. So, but the only difference is that instead of you taking all the columns, you do feature sampling. Okay. So that's the reason where you are introducing generalization to the data set. Okay. So instead of taking all the data points, I mean, all the futures. So for the first node, you will not consider all the data sets. Okay. You will not consider all the data sets. Thus, instead of considering all 4 variables to figure out how to spread the root node, you randomly select 2 nodes. In this example, we are only considering 2 variables. Okay. At each step, at each node, you're randomly selecting 2 nodes. Only 2 nodes are chosen or are selected. In this case, we randomly selected good blood circulation and blocked arteries as candidates for the root node. Okay. So instead of all the 4, in the second step, we only choose subset of the features for constructing a specific node. Here, we haven't considered chest pain and weight. We are considering only 2 rows. Okay. And then we are choosing this node. In this case, we randomly selected these 2. Okay. We will come back later to understand how many columns has to be considered for each station and how that value will be decided and all that stuff. But for this example, to just understand how do we do the feature sampling, just an example, instead of all the 4, I have picked only 2, and only these 2 columns are used to construct this node. Okay. Let's suppose once this node is constructed, okay, once this node is, let's suppose good, out of these 2 that we have chosen, good blood circulation and blocked arteries, good blood circulation is something that is having high information gain. Let's suppose this node is having high information gain. Then we consider that as a root node. And now out of the 3 columns that are available now, we again randomly pick 2 columns in this. Okay. At every step, we are only considering 2 random columns for constructing a particular road. Now we randomly pick chest pain and weight. When you pick randomly 2 columns, it can be anything. Chest pain, blocked arteries can also become chest pain, weight can come, blocked arteries and weight can come. Anything can be picked. That is random sampling. Okay, when you do random sampling, it's not in handshake what will come up. Okay, but you have to pick up that number is decided. Here we decided to pick 2 columns at every leaf node. I mean at every node. So here, just like the root, we randomly selected 2 variables as candidates instead of 3 remaining columns. Now, out of these 2, we again come up with, here we come up with something called a chest pain, let's say. And then we black out this chest pain. Now we have only two variables. Okay. Out of these 2, we again choose one, out of these 2, we again come up with only one variable again. I mean, with one node here. So we continue this process until we reach to a leaf node where a particular class is derived. Okay. That is how random sampling will be done. Random future sampling will be done without replacement, whereas bootstrapping is done with replacement. And out of bag data is used to test that particular model that is developed, or test the random forest that you have developed. Okay, if you look at this example, you will clearly understand what we are trying to achieve here. Okay, so the first step in random forest construction is, let's suppose this is the data set that is given for you, which is 6 by 6 matrix. Okay, this is the future label and you have 5 futures. And we are doing a bootstrap sampling. If you look at these IDs, when you're doing a bootstrap sampling, 5 repeated twice because you are doing the sampling with replacement, and every others came only once. And what haven't we got? We haven't got 6th sample in this. Okay, 6th sample is the out of bag data for this bootstrap sample 1. And okay, and we constructed a bootstrap sample 1. Similarly, we have constructed a bootstrap sample 2. But in this case, what are duplicates? 3 is a duplicate here. 3 came twice. Okay, 1, 2, 3, 5 didn't came up in this sampling, so 5 is the out of bag data set for this bootstrap sample 2. Once the bootstrap data sets are constructed, then what we have to do, construct the decision tree, right? For bootstrap sample 1, we construct one decision tree. Okay, for bootstrap dataset 2, we construct decision tree 2. If you're doing 1,000, if you're constructing 1,000 bootstrap datasets, we get 1,000 decision trees. And the random forest now consists of 1,000 decision trees. Now, when you want to classify a new data point, you feed this to 1,000 decision trees, and you aggregate the result coming out from all the 1,000 decision trees. Okay, that is what. For convenience, we are just taking 2 bootstrap samples, and we will construct 2 decision trees, and we take the aggregated results of that. The second step in this random forest is to construct the decision tree for every bootstrapped samples, right? So when constructing the decision tree, what you do feature sampling. Okay, feature sampling means out of 5 features that are available, we consider only 3 random features, 3 features randomly at each node. Okay, at each split, only a random subset of features is considered to determine the best split. Okay, now suppose we select 3 random features at each node. So the randomly we selected x1, x3, and x5. Okay, we are working on bootstrapped sample 1. Okay, we are working on bootstrapped sample 1, and now we picked, for constructing the root node, we picked 3 features. Those 3 features are x1, x3, and x5. We picked x1, x3, and x5, and we found out that the best split here. How do we come up with the best split? We construct all the possible subtrees for that particular node, and then we calculate the entropy for every node, and then we decide the best root node. We discussed this in decision trees, right? So the best split here is x3 less than or equal to 5. Now, once we decided that, we come up with left child and the right child. So when we decided x3 less than 5, so we decided this is the root node, x3 less than 5. That means this is less than 5, this is less than 5, this is less than 5. So these 3 points will be on one side, the rest of the points will be on other side. So what are the IDs that will be? So x3 less than 5. So it will be divided into 2 points. If it is true, what are the points they will be coming up? The IDs of the points will be 2, 3, and 1. Right? So 2, 3, and 1 will be on the one side. On the other side, what will be there? 5, 5, and 4 will be on the other side. 5, 5, and 4 will be on the other side. So if you look at this, 5, 5, 2, 4. 5, 5, 2, 4. Why 2, 4 here? 1, 3, 2, 4, x3, right child goes with x greater than 5. Is 5, 2, 5, 4. 5, 2, 5, 4. 5, 2, 6, 1, 3. I think there is something wrong here. This is bootstrap sample 1. All right. So I think we have 5, 5, 4. We don't have 2 here. 2 should come here. That's okay. Anyways, I'm just trying to give you an example. Now, so now we need to exclude x3. As we already picked this for the root node, we have to gray this out. We no more has to consider this for sampling, because feature sampling is not with replacement. And when you're constructing the right child, again you have to do a random feature sampling. So the remaining one is x2, x1, x2, x4, and x5. Out of these 4, you have to randomly select 3 features. Now when you randomly select 3 features, you got x2, x4, and x5. You got x2, x4, and x5. Again, when you divide that, you divided that as on the left side, you got x4. You got this as a best split. On the left side, we got 1, and the right side, we got 1. So 3, 3 and 1 is the IDs that we have got. And on the right side also, we randomly sampled 3 features again. Randomly sampling 3 features is again like you pick three features out of all the available one on the right side, and you come up with the best split and divide this in. So you continue this until this column sampling and extending, random column sampling without replacement extending will continue until leaf nodes are purely on stopping criteria or a stopping criteria is met. Leaf nodes are pure. That means they belongs to a particular class. So you construct this decision tree until that particular point. So you constructed one decision tree for bootstrap sample one. Similarly, you constructed a different decision tree for bootstrap sample two. For bootstrap sample two, you will get another decision tree, something of that sort till you get then, till you reach to something of that sort. Okay, for every bootstrap sample, you will have one decision tree. If you have 1,000 bootstrap samples, you will have 1,000 decision trees. Okay, then what is the next step? Once we constructed that decision trees, 1,000 decision trees, this is how the new data set, new point or the test will be constructed. So this is the out of bag sample, right? You have seen in the first slide that this is not picked for when this is not picked when we are doing a sampling with bootstrap, when you're constructing a bootstrap data set. So now that will be used to test that random forest. Okay, so now using this test data set, we actually test all the random forests that we have, all the decision trees that we have constructed for each bootstrapped sample. Let's suppose if we constructed, we derived 3 bootstrap samples and these are the 3 random forests that we have created. Okay, now if you fed this data to the decision tree one, it predicted that as yes, and when you fed this to the second data set, it predicted that as no, and if you fed that to the third data set, it predicted that as no. Now if you take, as this is a classification problem, yes and no, yes came once and no came twice, so we are going with highest voting, right? So as this is the highest voting in this case is with no, so we classify this as no. Okay, okay, that is how it actually decides that. If you look at this, so in this example, S came once and no came twice. Since a label with most votes win, it is the label that will be assigned to the out of bag. So no has the highest voting. So for this particular sample, we assign this as no. That is how you do the classification using random forest, which is an example of packing. When we then do the same thing for all the other out of bag samples for all the trees. Okay, let's suppose if we have 100 rows of out of bag data set, we do this for every row and we calculate the output or the label. We found out the label for all these data sets. Ultimately, we can measure how accurate or more random forest is by the proportion of out of bag samples that were correctly classified by the random forest. Like it's a normal thing. Again, now we do that for all the out of bag samples and then we calculate the accuracy. So the proportion of out of bag samples that are incorrectly classified is out of bag error. Let's suppose if this is classified as this, but this is the original classification for this is no, this is called as out of bag error. That means it didn't rightly predicted the label for that particular data set. So such kind of such kind of errors are called as out of bag errors. These are called out of bag samples, and the error, if we are getting errors in predicting that label of that out of bag errors, out of bag data sets, out of bag data point, we call that as out of bag error. Okay, now I was saying you like we picked 2 columns, right? What is the standard value? It's here we picked 2 columns, um, 2 columns sampled for every root node, right? Or every node in this tree. Why not pick 3 columns? Why not pick 4? How do we decide that value? We decide this value something like this. If you look at this, what this says is the random forest technically works like this. So we build a random forest, estimate the accuracy of the random forest, okay, and then change the number of variables used per step. Okay, now let's suppose you have used 2 steps here, right? You have used 2 columns, and then you created a random forest and calculated the accuracy. Now change that to 3 three columns or three features, construct a random forest and again calculate the accuracy. If the accuracy with three random variables is high, go with that. If the random if the accuracy with two features is high, you go with that. Do this for bunch of times and then choose the one that is more accurate. Okay. So you repeat this process for n number of times and choose the feature number which is more accurate. So basically the number of features considered at each split, the number of features considered at each split would be equal to root p for classification, p by 3 for regression problem, where what is p is nothing but number of features. Here in this case we have 4 features. As this is a classification problem, we start with root 4, which is 2. We consider 2 features for each split. Okay, and calculate the accuracy, and then go to 3, calculate the accuracy, go to 4. So you move around this value and find out the best fit by doing by calculating the accuracy for different values of this different number of features considered at each split, and then finally decide what is the best best number of features that needs to be considered at each split. You will get based on the accuracy you calculate for each of those splits. That is an example of bagging. Okay, random forest is an example of ensemble learning bagging, where you combine multiple decision trees and then based on the voting, majority voting at the end for classification, we assign that particular class to that variable. The important terminologies that we have covered over here is bootstrapped sampling, that is row sampling with replacement, and future sampling. Future sampling is nothing but sampling the columns without replacement. How many columns has to be considered at each split? For classification, it is root p. So root p number of features has to be considered at each split, and if that is classification, p by 3 number of features has to be considered at each split. But that is not constant. You try this, or you try that with multiple number of splits around that root p to find out the best value for the or the to find out the number of features that needs to be considered at each split by going by calculating the accuracy at each step. Or okay, we do that for a bunch of times, and then choose the number of variables used per step based on the accuracy that we have got. So this is all about random forest. We combine multiple decision trees, and based on the voting, we are getting the value we are assigning the value or getting the value for the regression problem, which is matching this bagging technique that we have discussed. Okay. If you look at this, everything is, if you compare this with the random forest, each data set is a bootstrap data set. Each base model is a decision tree. And if this is a classification problem, we take the voting for the classification and predict the value of that as that particular class. If the regression problem, we take the average. Okay, that is what random forest classifier. That is how random forest classifier basically works. And boosting we will discuss tomorrow, because under boosting only we get that ADA boost, gradient boost, and XC boost. I'll cover all of them tomorrow. But we will talk about stacking. Okay, I'll also give you an example tomorrow, which I have to prepare a slide for that. I'll do that. But let's get the basic technique behind stacking. How does stacking actually works? Okay, so stacking is something that works like this. So how does stacking basically works is, stacking involves training multiple models. In ensemble learning, it involves always multiple models. Okay, in stacking, so this is a last slide, bear with me for a few more minutes. In stacking involves training multiple models, multiple base models. That is what ensemble learning is. Stacking is a type of ensemble learning, and we expect that. And then combining the predictions using another model. Okay, you will understand this shortly. Combining the predictions of the base models using another model and then combining their predictions using another model, the meta model. The meta model learns how to best combine the predictions of the base model. That is what stacking is. So this is the training data set. We construct different bootstrap data sets from this training data set, and we train different models, and the output of these models is used or is fed to this meta model, and this meta model finds the best way of combining the outputs of these models to do the final prediction. Okay, if I have to tell you an example, let's suppose this is let's take an example. Let's suppose the model one is called as logistic regression. This is just think this as one of the models. You don't necessarily need to know what is logic regression at this point of time. Let's say model one is logistic regression, model two is decision tree, and the model three is random forest. We just learned. So these are the three models that we have chosen, and we constructed bootstrapped data set, and we fed that bootstrapped data set to every model. Okay, now every model came up with an output. Okay, every model came up with an output. Okay, that output is constructed as the data to this meta model. How does that output actually looks like is, if you look at this, okay, each model is trained on the training data set, and the predictions are made on the validation set. Now, until this point, we learned that the data that is given for us is divided into two sets. One is training set, and the other one is test set. So that is what we have learned so far, right? 80% is of the training data set and 20% is of the test set. Now, this breakdown is done further into three sets for this stacking process. For this tracking process, what we do is, given the data, we split that into three parts. One is training data set, one is training, and the second one is validation set. Second one is validation set, and the third one is test set. Okay, this validation set is something which decides the input for this meta model. Okay, we train these models using the trained data set of the bootstrapped data set. Once this is trained, this validation set would be fed to this model. Okay, that output given for that model, for this validation set, will be captured in a table. Okay, let's suppose we have 5 points in this validation set. For 5 different points, the model one gave this output 0 0.8, 0 0.6, 0 0.3, 0 0.2, 0 0.9. Okay, and the decision tree gave the output as 1 0 1 1 1 1 0 0 1. And now random forest gave the output for these validation sets as 0 0.9, 0 0.7, 0 0.4, 0 0.1, 0 0.1, 1.0. And the labels for all those validation sets are placed as an fourth column. Okay, that is how the new training data set for the meta model will be created. So the outputs of these models are fed to this meta model. Okay, so now what will this meta model do is, the predictions from the base model now become the features for the meta model. The true labels remains the same. The validation data sets true labels will remain the same. Now, what this meta model will do is, it decides the weight that needs to be given for the output of the each model. Okay, based on the outputs that they have given. Okay, based on this data set, you again apply one model. This can be again decision tree or logistic regression or random forest. This is also another classification model. What this classification model will do is, okay, a linear model, whatever it is, this is also another machine learning model. What this model will do is, it comes up with an equation. It can also be an SVM. So SVM is nothing but a weight vector. Weight vector decides how the input features has to be combined, how the x1 x2 x3 has to be combined. Now, this meta model will combine the outputs given by, it decides the weight that has to be given to the outputs of each model. Let's suppose the meta model learns how to optimally combine them to make predictions. To make the best predictions, this meta model will try to find out the weights that needs to be given for these models. If you look at this example, in this example, it gave 0.6 weightage to base 1, the logistic regression, 0.3 weightage is given to decision trees, 0.1 weightage is given to the random forest. That means high weightage is given to the output of the model 1, and the second highest weight is given to the model 2, and the third highest weight is given to the model 3. So combining all these things, it will come up with the final prediction. That is what actually stacking means. Okay. If you really understand this, so again, I'm repeating. So you have three sets of data right now. Okay, one is again validation set and test set. Once the model is developed, the accuracy or other parameters will be calculated using the test data set. You still have the test data set, right? The test data set will be fed to the whole model now, and then accuracy will be calculated to see how the total model will be working. But to construct this particular data set, we come up with something called as validation set. That validation set is used to construct this new training set. Okay, I'm repeating for one last time. So we have this data set. This will be constructed into three parts. One is train, one is validation, one is test. Train is used to train the models. Once the models are trained, let's suppose I have 100 records. I got, let's suppose, let's take simple number, not such big number. Let's take 20 records. That would be good. That will be in sync with this. So let's take 20 records. Out of 20 records, 10 records are used to train the data set. 5 records are for validation, 5 records are for test. Okay. Using these 10 records, we train the models. We train model 1, we train model 2, we train model 3. Once these models are trained, these 5 points are fed to the model. Okay. So every model will get a different data set. Okay. Every model will get different bootstrap data set, not the same data set. So now these 5 points belonging to bootstrap data set 1 will be fed to this. So this will make 5 predictions for these 5 points. So logistic regression came up with 5 different values for that particular 5 points. For the bootstrap data set 2, the decision tree came up with 5 values. 5 values are like decision tree comes up with a class, right? Decision tree comes up with a class, to which class it has to be assigned to. Okay, let's suppose for the first point it assign class 1, second point it assign class 1, third it assign class 0, fourth it assign class 0, fifth it assigned class 1. Okay, that means these are the outputs of the decision tree. Outputs are the class assignments of the decision tree. Random forest came up with the probabilities of a specific class. Okay, that means these probabilities are nothing but random forest is just a combination of different decision trees, right? So it also has to come up with a particular class that depends on the majority voting. But here it calculated the probability of, if you look at this, why it is 0.9, it has to be as 1 0, right? Class 1 or class 0. But why 0.9 means sometimes random forest, what it will do is, let's suppose class 1, class 0. Voting for class 1 is 5. Voting for class 0 is 3. So it is representing the probability of class, not the majority voting. What it will do is, the probability of class 1 is 5 by 5 plus 3, which is 5 by 8, which is something like 0.6 or something, right? So that is what this probability is. So that's the reason you might wonder, as random forest is just a combination of different decision trees, and we decided the prediction using the highest voting, then why do we see 0.9 is something that you will come to know. But here this 0.9 is nothing but the probability of assigning the point to a particular to class 1. That probability is calculated just by the voting given for the voting given by different weak learners or different decision trees in random forest to class 1 by total number of um, points. I mean total number of random forests or total number of weak learners. So this is the output given for 5 validation points by the model 3. Now we combined all these things and also appended the true labels for all these 5 validation points. Okay. So I think I spoke something wrong. So we feed the same training set for all the models here, not different bootstrap dataset. The same training dataset will be fed to all the models, not different bootstrap datasets. Okay. Same training set will be fed to all the models. Okay. In stacking, we fed the same training dataset. We don't do the bootstrap sampling. Okay, just a correction there. So that we got the true labels. We also append the true labels for all the classes, and now we have this new training set. This training set will be fed to this a new model which is called as meta model, and this is called as meta. I mean another model called as meta model. The major role of this meta model is to predict the weightage for the different outputs. Okay, predict the weightage for different outputs. So this meta model will give the weightage based on the data that is fed to it. It gives the weightage for the weightage of this model. It also tries to find out the weightage for this model. It also calculates the weight for this model. So it can be SVM. SVM, what it actually tries to do, h of x is equal to w transpose x, right? So x is nothing but the inputs given to it. So this is the x vector, x1, this is x2 vector, this is x3 vector, this is x4 vector, this is x5 vector. Okay. So it tries to find out the weight one, w1 x1 plus w2 x2 plus w3 x3 plus w4 x4, right? Something like this. So it tries to come up with this weight vector if this model is SVM. So now we came up with a single equation. So in this case, for base 1, for model 1, the weightage is 0.6. For model 2, and for model 4, the weightage is 0.1. So highest preference is given for the model 1. So now when you get a new point, and now you test this model with the test data set. So the test data set will be fed to this model. So it comes up with an output, it comes up with an output, it comes up with an output. So now the final prediction is made based on the outputs that we're getting. So we get the probability of class 1 for this is for example, for base 1 we got something like again 0.8. We got this as 1. We got this as 0.9. So we come up with the final prediction based on that. Okay, I'll show you an example tomorrow by taking a sample data set and by walking through how the final prediction is made. But stacking is something that this is the process how the stacking actually works. Okay, that's all for today.